Hello there, and welcome to Space Sleep Journey, where curiosity takes the gentle shape of a bedtime story and science moves at the pace of a quiet breath. I am so glad you are here tonight, whatever hour it is where you are, whatever kind of day is finally letting you go. There is nothing left for you to do now, but settle in and let your mind wander somewhere soft and far away. Tonight, we will be wandering toward one of the strangest questions in all of space. What is a Thorne-Zytkow object, really? What does it mean for a dead star, a collapsed neutron star only about 12 miles across, no wider than a small city, to be buried and still burning inside the swollen red heart of a giant star? And how could we ever from here tell such a hidden monster apart from an ordinary giant? It is a question about a star with a corpse for a heart, and about how patient people have tried for nearly 50 years to find one. We are going to take it very slowly. Before we begin, I find myself wondering where you are listening from tonight. Perhaps you are lying in a bright city, where the glow of the streetlights washes the stars from the sky, and the night above the rooftops is a soft and empty orange. Or perhaps you are somewhere quiet and far from any town, where the dark is deep and complete, and if you stepped outside, the Milky Way would spill overhead like a great pale river of light, and low in the south, you might even find a faint dim smudge that is a whole other galaxy. Wherever you are, in the bright city or the quiet countryside, you are part of a small quiet company tonight, all of us settling into the dark together, all of us about to wonder at the same strange star. If you find, as the night goes on, that this slow voice is a comfort to you, I would be grateful if you tapped like or subscribed, so that others who need a quiet voice in the dark can find their way here too. There is no hurry. You could do it now, or in the morning, or never at all. It changes nothing about tonight. Tonight is yours to rest in. Now take a breath, a slow one, all the way in, and let it go. Settle into your chair or your pillow. Let your shoulders soften and your hands lie still, and let the weight of the day begin to slip away. There is nowhere you need to be, and nothing you need to solve. We are only going to wander slowly toward a strange and distant star, and let the wandering carry us both down towards sleep. Imagine the night is clear and cool, and the stars have come out one by one until the whole sky seems to be listening. Imagine you could rise up from where you are lying, gently, without any effort, and drift out past the rooftops, past the clouds, past the pale glow of the moon, out into the deep dark between the stars. And imagine you drift a long way, farther than any road could ever carry you, farther than light itself can travel in all of recorded human history, until you come at last to a great red star, an old and gentle giant, glowing softly in the black like a banked ember in the last hour of the night. From the outside it looks calm and ordinary and vast beyond all sense. Deep within it, where the burning heart of a star should be, something else is waiting. Something small. Something impossibly heavy. Something that was once a sun of its own, and then died, and yet did not go out. Let us drift toward it now, slowly, together, and see what such a thing could possibly be. Imagine the night is clear and cool, and the stars have come out one by one until the whole sky seems to be listening. Somewhere out there, farther than any road could ever carry you, there may be a star that is not quite a star. It looks like an old and gentle giant, a great red lantern hanging in the dark. But deep inside it, where the heart of a star should be, something else is waiting. Something small. Something heavy. Something that used to be a sun of its own and then died, and yet did not go out. Tonight I want to sit with that quiet impossibility for a long while. I want us to walk around it slowly, the way you might walk around a strange old house at dusk, looking in one window and then the next, trying to understand what could possibly live inside. And the thing living inside this house is a corpse. A dead star. A heart that stopped, buried in the chest of a star that is still alive. Let us begin with the outside, because the outside is the trick. From far away, this object would look almost ordinary. It would look like a red supergiant, one of the largest kinds of star the universe knows how to make. If you have ever heard the name Betelgeuse, the great red shoulder of the hunter in the winter sky, then you already have a picture in your mind. A red supergiant is a star grown old and swollen, puffed up to a size that is hard to hold in the imagination. Glows a deep, warm red, the colour of an ember that has been breathed on. It is cool at the surface, as stars go, and enormous beyond all sense. And that is exactly what this strange object would seem to be. If you pointed a telescope at it and you did not look too closely, you would write down in your notebook that you had found another red supergiant, one more great red lantern among the many. You would move on. You would never guess. Because the strangeness is not on the surface. The strangeness is hidden at the very center, folded away under hundreds of millions of miles of glowing gas, where no eye and no telescope can ever look directly. That center, where a normal giant would have its own burning core, there is instead a neutron star. And to understand why that single fact is so quietly astonishing, we have to understand what a neutron star actually is. So let us step back for a moment, the way you step back from a painting to see the whole of it. When a large star comes to the end of its life, it can die in a tremendous collapse. Core falls inward on itself, faster than you could blink, and it is crushed down under its own weight into something almost unbelievably dense. Protons and the electrons of ordinary matter are pressed so hard together that they merge into neutrons, and the whole core becomes a single, smooth, impossibly tight ball of them. That ball is the neutron star. It is what is left of a star's heart after the star itself has been blown away. And here is the part that is hard to feel in the body, because the numbers are so far outside anything we ever touch. A neutron star is only about 12 to 15 miles across. That is smaller than many cities. You could drive from one side of it to the other in the time it takes to finish a short errand, if there were any road and any car, and any way at all to survive being near it. It is a ball you could lay across a single county and have room to spare. And yet, into that tiny ball, nature has packed more than the entire mass of our sun, more than the mass of the star that gives us every warm day we have ever known. The usual figure is about 1 4/10 times the mass of the sun, all of it squeezed into a sphere the size of a town. Think of that for a moment. Everything the sun is, all of that weight and pull and substance folded down until it would fit inside the space between your home and the next town over. There is an old way of trying to feel this, and I want to offer it to you now, softly, because it is the kind of thought you can lie still with. Imagine you could reach into a neutron star and scoop out a single sugar cube of its matter. Just one small cube, the kind you might drop into a cup of tea. That one little cube, no bigger than the tip of your thumb, would weigh about as much as a whole mountain. Not a boulder, not a hill, a mountain. One spoonful heavier than a peak you could see from miles away. That is the thing sitting at the center of our strange star. A city-sized ball, denser than anything you will ever hold, with the weight of a sun inside it, and the pull of gravity at its surface so fierce that it bends the very light around it. This is the dead heart. This is the corpse in the chest of the giant. Now hold both pictures in your mind at once, gently, side by side. On the outside, a red supergiant so vast that its numbers stop meaning anything. On the inside, a neutron star so small it would be lost in a single one of our states. The largest kind of star we know, wrapped around one of the smallest and heaviest objects the universe can build. A giant with a dead star for a heart. Marriage of the enormous and the tiny is the whole mystery of tonight. Astronomers call it a Thorne-Zytkow object, after the two people who first dreamed it into the language of physics, and we will come to them soon. Before we do, I want to stay in the wonder of the shape itself, because the shape is what makes this object almost unbelievable. Let me try to give you the scale of the outside, the way you can feel it. Our own sun, the star we know best, is already almost too large to picture. If the sun were a beach ball, the earth would be a small seed sitting a good distance away. More than 1 million earths could fit inside the sun. And still, on the scale of stars, the sun is modest. It is an ordinary yellow star, middle-aged and calm. A red supergiant makes the sun look like a grain of sand. These stars are hundreds of times wider than the sun. Some are so large that if you sat one down where the sun sits, its glowing surface would reach out past the orbit of Mercury, past the orbit of Venus, past the Earth, and swallow the orbit of Mars. The whole inner solar system, all the little worlds we know, all the ground we have ever stood on, and all the ground we have ever dreamed of standing on, would be inside the star. It would not be near the star. It would be within it, drowned in the outer layers of a single sun. So when I say the neutron star is buried inside the supergiant, I want you to feel the true distance of that burial. The dead heart is not just below the surface the way a stone is below the skin of a pond. It is at the center of something wide enough to hold a planetary system. The glowing gas above it stretches out for hundreds of millions of miles in every direction. Light itself, the fastest thing there is, would take a long, slow while to climb from that center up to the surface and out into the night. The corpse is buried deep. It is buried under a whole star. And here is what makes it stranger still. That outer envelope, the great red body of the giant, is almost nothing. It is enormous, yes, but it is thin. The gas out near the surface of a red supergiant is spread so wide and so faint that in many places it is thinner than the air you are breathing right now. It is closer to a vacuum than to anything you would call solid. If you could stand at the edge of such a star, and if the heat did not undo you at once, you might reach out your hand and feel almost nothing at all pass between your fingers. So picture it truly. A ball of matter so dense a spoonful weighs a mountain, resting at the center of a cloud of gas so thin it is nearly empty. The heaviest thing imaginable, wrapped in the lightest. The most crushing density we know of, cradled inside the gentlest haze. That is the Thorne-Zytkow object. That is the creature we are visiting tonight. A heart of impossible weight, floating in a body of almost pure emptiness. I find that I have to say it more than once to believe it. So let me say it another way, and you can let the words settle over you like a blanket being drawn up. Somewhere, perhaps, there is a star the size of a solar system, red and slow and old. And at the very middle of it, hidden from every telescope we will ever build, there is a dead sun the size of a city, still holding within itself the mass of a living one. The giant looks alive. The giant glows. And it glows in part because of the dead thing at its center, which is the deepest strangeness of all, and one we will spend a long time on before the night is through. For now, let this be enough. A star with a corpse for a core. A body of gas around a heart of crushed matter. Something that, by every ordinary rule of how stars are supposed to work, should not really hold together the way it does, and yet the physics says could. That word could is going to matter a great deal tonight, and I will keep coming back to it gently, because we are walking a careful line between what the laws allow and what we have actually seen. But we are not there yet. For now, we only have the image. A giant. A dead heart. The light's still on. Let us keep looking. So what would it actually be like, this object, if you could somehow drift toward it across the dark and see it grow from a point of light into a world? First, it would be only another red spark among the thousands, indistinguishable, humble. As you came closer, it would swell into a soft red disk, the colour of an old coal, wide and calm. Closer still, and it would fill your view, a wall of dim ember light stretching from one edge of everything to the other, so large that you could no longer see it as a ball at all, only as a glowing sky that went on and on. And nowhere, at any point in that approach, would you see the secret. There would be no mark on the surface, no scar, no bright wound over the place where the dead heart lies. The neutron star gives away nothing to the eye. It sits at the centre in perfect hiding, and the only sign that it is there at all, the only sign in the entire universe, is written faintly into the colour of the light, in a code so subtle that it took us decades to learn how to read it. We will learn to read it too, tonight, slowly, together. But first we must understand how such a thing could ever come to be. How do you put a dead star inside a living one? How does the corpse get into the chest? That is where we go next, and it is a story of two stars and of a slow and patient fall. Before we follow the corpse into the chest of the giant, I want you to meet the two people who first saw this creature, not through a telescope, but with pencil and paper and the quiet machinery of physics. Because this is one of those rare things in science that was imagined long before it was ever looked for. It began as a question in someone's mind, a what if, and only much later did anyone go hunting for it in the sky. The year was 1975. A physicist named Kip Thorne, who worked at the California Institute of Technology, and a young astronomer named Zytkow, who had come to work alongside him, sat down together with a question that most people would never think to ask. What would happen, they wondered, if you took a neutron star, one of those tiny crushed remnants of a dead sun, and you placed it not out in empty space, where such things usually drift, but down at the very centre of another, ordinary star? What would that other star become? Could it even hold together at all? And if it could, what would it look like from the outside? They worked it through, layer by layer, in the careful language of equations. And what they found was that such a thing was allowed. The laws of physics did not forbid it. You could, in principle, have a star with a neutron star for a core, and the outer star would puff up into a red supergiant, cool and enormous and red, and it would go on shining, drawing its light not from the usual fire at its centre, but from stranger sources entirely. They published this first in 1975, and then in a fuller and deeper study in 1977, they laid out the structure of these objects in detail. And so, quietly, in the pages of a scientific journal, a new kind of star was born, made not of gas and fire, but of mathematics. The name came later, from the astronomers who followed this line of thought. They called these hypothetical creatures Thorne-Zytkow objects, joining the two names together, the way you would join the two stars that make one. And I want to pause on that word, hypothetical, because it is the truest word in the whole story. For decades, and in many ways still today, a Thorne-Zytkow object was a creature that lived only in theory. It was something the universe should be able to build. It was something the laws allowed. But no one had ever pointed to a patch of sky and said with certainty, there, that one, That is a star with a dead heart. It was a prediction waiting for a discovery. A shape drawn in equations, hoping to be found in light. Kip Thorne, by the way, would go on to become one of the most celebrated physicists of his age. Many years after this early work, he shared in the highest honour his field can give, a Nobel Prize, for his part in the first direct detection of gravitational waves, the faint ripples in the fabric of space that wash out from colliding black holes and neutron stars. So, the same mind that helped us feel those ripples had, decades earlier, dreamed up this buried creature. And Anna Zytkow, his partner in that early dreaming, would stay close to the search for these objects for the rest of her career, right through to the day, many years later, when a candidate was finally announced, and her name was on the paper that announced it. There is something gentle in that. She helped imagine the creature as a young astronomer, and she was still there, decades on, to help point at the best example anyone had ever found. We will come to that night. Not yet. For now, let us go back to the two stars, and let us really feel the strangeness of the pairing, because it is the heart of everything. A Thorne-Zytkow object is a marriage of two things that could hardly be more different. Joins the very small to the very large, the very heavy to the very light in a single body. And the contrast between them is so wide that it is almost hard to believe they belong to the same object at all. On one side of this marriage is the neutron star. We have already sat with its numbers, but let me lay them beside its partner so you can feel the gap. The neutron star is only about 12 to 15 miles across, a ball you could rest across a single city. It holds within it more than the whole mass of our sun, packed to a density so extreme that a thimble of it would outweigh a mountain range. Its gravity is so strong that if you dropped a single marshmallow onto its surface from far away, the fall alone would release the energy of a great bomb. It is small, and it is dark, and it is unspeakably heavy. It is the corpse. On the other side of the marriage is the red supergiant envelope, the great body of gas that surrounds the corpse. And this thing is the opposite in every way. Where the neutron star is tiny, the envelope is vast, hundreds of times wider than the sun, wide enough, as we have said, to swallow the orbit of Mars if it sat where the sun sits. Where the neutron star is dense past all imagining, the envelope is thinner than air, closer to emptiness than to substance. Where the neutron star is dark, the envelope glows across the whole face of the night. One is a clenched fist. The other is a held breath. And they are the same star. I keep returning to this because I think it is the thing worth falling asleep on. A city drowned inside a solar system. A mountain-heavy spoonful hidden in a cloud you could almost see through. Two ends of what matter can do, the crushed and the diffuse, brought together in one quiet object hanging in the dark. If you built a scale model where the great red envelope was as wide as a football field, the neutron star at its center would be far smaller than a single grain of sand, set down at the 50-yard line. And that invisible grain of sand would weigh more than the entire glowing field around it. That is the object. That is what we're trying to understand. And it raises the obvious question, the one that any child would ask, the one that is exactly the right question to ask. How? How on earth, or rather how out in the depths of the sky, does a dead star end up buried at the center of a living giant? Neutron stars are not born inside other stars. They are born alone in the violent death of a massive sun flung into being by an explosion. So how does one of them come to rest, quiet and hidden, at the very core of a great red star that is still shining? Corpse has to get into the chest somehow. And the leading answer to that question is a slow, strange, and rather beautiful story of two stars orbiting each other, and of one of them falling, over a long age, into the heart of the other. Let us follow that fall. It begins, as many stellar stories do, with two stars born together. Out in a great cloud of gas and dust, where new stars come into being in litters and clusters, it often happens that two stars form side by side, close enough to fall into orbit around each other. They become a binary, a pair, two suns circling a shared center, bound together for the rest of their long lives. This is not rare. A great many of the stars you see in the sky are not single at all, but are pairs, or even families of 3 and 4, wheeling slowly around one another in the dark. So begin there. Two massive stars, born together, orbiting close. The more massive a star is, the faster it burns through its life. It is a hard rule of the sky, and a strangely human one. The biggest, brightest, most furious stars are the ones that die youngest, spending themselves in a brief and brilliant age, while smaller, calmer stars live on for a very long time. So, in our pair of stars, one is likely a little heavier than the other. And that heavier one will reach the end of its life first. It will run out of the fuel at its core, and its core will collapse, and the star will die in a supernova, one of the most violent events the universe knows how to stage. In that explosion, the outer layers of the star are blown away into space, and the crushed core is left behind as a neutron star. So now the pair is changed. Where there were two living stars, there is now one living star and one dead one. A neutron star, tiny and heavy and dark, still orbiting its living companion, still bound to it by gravity, circling on through the years as if nothing had happened, as if it had not just died. Corpse and the survivor wheeling together in the dark. And the survivor, for now, goes on with its life, still burning steadily, unaware, if a star can be unaware, that its partner is now a ball of crushed matter the size of a town. Time keeps moving, as it always does. And in its own turn, the surviving star begins to grow old. Burns through the fuel at its own core, and as it does, something strange and grand happens to it. Something that happens to nearly every star of its kind. It swells, Its outer layers puff up and expand further and further, cooling as they spread, until the star has ballooned into a red supergiant, one of those great red lanterns we have been speaking of all along. Grows and grows, reaching outward across millions of miles, then hundreds of millions. And the tiny neutron star, its dead partner, is still there, still circling. But now it is circling a star that is swelling toward it. The giant is reaching out. And soon, perhaps, it will reach far enough to touch its own dead child, and then to swallow it. And that swallowing is where the true strangeness begins. Picture the moment the giant grows large enough to reach its dead partner. The neutron star has been circling at some comfortable distance for ages, a small dark point tracing its patient orbit. The giant is expanding, its glowing edge creeping outward year by year, and there comes a day when that edge finally reaches the orbit of the neutron star. And on that day, the neutron star is no longer circling in clean, empty space. It is circling inside the outer layers of the giant itself. It has entered the star. The two of them now share a single body of gas, and astronomers have a plain and lovely name for this state. They call it a common envelope. Two hearts inside one skin. And once the neutron star is inside that envelope, everything changes for it. Until now it has been moving freely, and an object moving freely through empty space keeps its orbit forever, circling on without losing anything. But gas is not empty space. As the neutron star ploughs through the thin outer layers of the giant, it feels a drag, a gentle friction, the same kind of resistance you feel when you wade through water instead of air. That drag is soft, almost nothing at any single moment. But it never stops. Every second, the neutron star gives up a little of its energy to the gas it is pushing through. And an orbiting body that loses energy does not slow and drift. It falls inward. It spirals down. So begins the long fall. The neutron star, once a distant companion, now sinks slowly toward the center of the giant, circling as it goes, tracing a great slow spiral inward through the body of the star. It is not a plunge. It is a settling, an easing down through the layers, over what may be a very long stretch of time. Round and round it goes, a little deeper with each turn, drawn down toward the core by the endless soft resistance of the gas. And as it sinks into denser and denser layers, the drag grows and the fall quickens until at last the neutron star arrives at the very center of the giant, the place where the giant's own core waits. And then the two cores meet. The neutron star, that crushed an ancient corpse, sinks into the living core of the giant and merges with it, or settles at its center, and takes the place where a normal star keeps its own burning heart. The corpse is now in the chest. The dead star is buried at the center of the living one. And what stands there, once everything has settled, is the thing we have been circling all night. A red supergiant on the outside, calm and enormous and glowing. A neutron star at its heart, hidden and heavy and dark. A Thorne, Zytkow object, made not in a moment but over a long, slow age of falling. I want you to notice how gentle that violence is in the end. It begins with a supernova, one of the loudest events in all the sky. The making of the buried creature itself is quiet. A slow spiral. A soft and endless drag. Patient sinking through the layers, round and round, deeper and deeper, until the two become one. There is something almost restful in it, if you do not think too hard about the forces involved. A dead thing, drawn slowly home into the center of a living thing and folded away there, out of sight. This is the leading idea for how a Thorne-Zytkow object could form, and I want to be careful with my words here, because this matters. It is an idea. It is a model. It is a story built from the laws of physics and from computer simulations of how stars behave. No one has ever watched it happen. No one has ever seen a neutron star spiral down into the heart of a giant, because it would take far longer than any human life, or indeed than all of recorded human history, to watch even a small part of such a fall. What we have is the physics, and the physics says this could happen, and that the common envelope, the shared skin, the slow spiral, is the most natural path to it. But it is a path we have reasoned out, not a path we have witnessed. Hold that lightly as we go. Every step of this formation story is a should and a could, never a saw. And there is a second path, a different way the corpse might find its way into a chest, and I want to give it to you too, because the honest picture includes both, and neither one is proven. This second path does not need two stars born together at all. Instead, it needs a crowd. There are places in the universe where stars are packed together far more tightly than they are around us. In our own quiet corner of the galaxy, the stars are lonely things, separated by distances so vast that light itself takes years to cross from one to the next. If the sun were a single grain of sand, its nearest neighbor would be another grain of sand miles away, with nothing but emptiness between. Our neighborhood is spacious. It is calm. Stars almost never come near one another here. But in the dense hearts of great star clusters, it is not like that at all. There, in what are called globular clusters, or in the crowded cores of other dense groupings, hundreds of thousands of stars are gathered into a relatively small space, all bound together by gravity, all wheeling around a shared center in a slow and ancient dance. In those crowded cores, the stars are close enough that near misses and even collisions, which almost never happen in a quiet place like ours, become possible over the long ages. Stars can pass close to one another. They can swing around one another. And sometimes they can capture one another. So imagine, in such a crowded place, a lone neutron star, a corpse drifting through the dense throng, one small dark remnant among the many stars. And imagine it passing close to a great red giant. In the open emptiness where we live, the two would simply sail past each other and part ways forever. But in the crowd, with other stars nearby to complicate the dance, the neutron star can lose enough energy, or be nudged just enough, that instead of sailing past, it is caught. It falls into the outer layers of the giant. And once it is inside, the same slow story begins again. The drag, the spiral, the sinking, the long fall to the centre. And at the end of it, once more, a Thorne-Zytkow object, made this time not from two stars born as partners, but from two strangers thrown together in a crowd. So there are two roads to this creature, as far as we can reason. One is the road of partnership, of two massive stars born side by side, one dying and being swallowed by the other as it swells. The other is the road of chance encounter, of a lone corpse captured by a giant in the crowded heart of a cluster. And I want to say again, as plainly as I can, that both of these are ideas. Both are models. Neither has ever been seen to happen. We do not know for certain that the universe makes these objects at all, and if it does, we do not know for certain which road it prefers, or whether it uses both. These are two competing stories, and the honest thing to say tonight is that they are stories we find plausible, not events we have watched. That honesty is not a weakness in the science. It is the science. This is how we come to know the sky, by reasoning carefully from what we understand, by building models, by saying clearly what is firm and what is guessed. And the Thorne-Zytkow object is one of those beautiful cases where the reasoning ran far, far ahead of the seeing. We could describe the creature in detail, its structure, its size, its two possible births, long before we had any example of it in front of us. In a way, we drew a careful portrait of something we had never met, from the laws of nature alone, and then we went out into the night to see whether nature had ever actually painted the same thing. But now a new question rises, and it is perhaps the strangest and deepest question of all. Suppose one of these objects does form by one road or the other. Suppose there really is a neutron star sitting at the centre of a red supergiant. What keeps the whole thing shining? A normal star shines because of the fire at its core, the fusion that turns light elements into heavier ones and pours out energy as it does. But this star does not have a normal core. It has a corpse where the fire should be. So where does its light come from? What feeds the glow of a giant with a dead heart? That is where we turn next, and it is the deepest strangeness of the whole strange creature. To feel why this question matters so much, let us remind ourselves how an ordinary star makes its light, because the Thorne-Zytkow object breaks the ordinary rule in a way that is easy to miss and important to understand. A normal star, like our sun, shines because of what happens at its centre. Deep in the core, the weight of all the layers above presses down so hard, and the temperature climbs so high, that the lightest element of all, hydrogen, is forced to fuse together into the next element, up, helium. And when it fuses, a little bit of matter is turned into a great deal of energy. and that energy works its slow way up through the star and out into space as light. That is the fire at the heart of every ordinary star. That is what a star is, in the simplest telling. A great ball of gas held up against its own gravity by the fire burning at its centre. Take away the fire, and the star should fall in on itself. But the Thorne-Zytkow object has no such fire at its centre. Where the fusing core should be, there is a neutron star, a corpse, already burned out, already collapsed. So by the ordinary rule, this object should not be able to hold itself up. It should have no engine, and yet the physics says it can shine anyway, that it can hold together and glow for a good long while, drawing its energy from sources that no ordinary star ever uses. And there are two of these strange engines, and which one runs depends, remarkably, on how heavy the outer envelope is. Let us take them one at a time, slowly. The first engine is the simpler one, and it powers the lighter of these objects, the ones whose outer envelope holds less than about 8 times the mass of the Sun. In these lighter objects, the light comes from falling. Matter from the great envelope drifts down toward the neutron star at the centre, drawn by that fierce, crushing gravity we have already sat with. And as that matter falls, it picks up tremendous energy, the same way a stone dropped from a great height arrives at the ground, moving fast and full of force. But the neutron star's gravity is so much deeper than any cliff or any well, that the matter falling toward it gains an almost unimaginable amount of energy on the way down. When it finally arrives near the surface of the neutron star, that energy has to go somewhere, and it comes out as heat and light, pouring back up through the envelope and out into the night. Astronomers call this process accretion, which simply means the gathering of matter onto a body by its gravity. And it is one of the most powerful ways the universe has of making light. Falling, it turns out, can be a furnace. When matter falls onto something as dense and deep-welled as a neutron star, the energy released can rival or even outshine the fusion fire of an ordinary star. So in these lighter Thorne-Zytkow objects, the picture is this. The dead heart does not burn, but it pulls. And the pulling, the endless slow rain of the giant's own gas down onto the tiny corpse at its centre, is what lights the whole thing up. The star shines by feeding its own dead heart. There is something quietly haunting in that. The giant glows because, drop by drop, it is falling into the grave at its own centre. The second engine is stranger still, and it powers the heavier of these objects, the ones whose envelopes hold more than about 14 times the mass of the Sun. Though the exact dividing line is a matter of ongoing study, and some of the work puts the threshold for a fully churning envelope a little lower, above roughly 12 solar masses. In these heavy objects, the envelope is so massive, and it churns so thoroughly from top to bottom, that a new and exotic kind of burning becomes possible at the searing hot region just above the neutron star's surface. And this is the engine that gives the Thorne-Zytkow object its one true fingerprint, so I want to walk through it with real care. Down near the neutron star, the the temperature is not like the temperature at the center of an ordinary star. It is far higher, driven up by the crushing gravity and the density of the corpse below. And in that ferociously hot layer, a rare kind of nuclear process can run, one that does not happen in the calm cores of normal stars. It has a long name, and I will give it to you and then translate it, because the name itself tells the story. It is called the interrupted rapid proton process, and astronomers shorten it, when writing, to a small handful of letters that we will not need to spell out here. Let us just call it, in plain words, the rapid proton process, the interrupted kind. Here is what it means. In this searing layer, atomic nuclei are bathed in a flood of protons, the tiny positive particles that sit at the heart of every atom. And these nuclei capture protons very quickly, one after another, faster than they can settle down between catches, building themselves up into heavier and heavier elements at a rapid pace. That is the rapid proton part. The interrupted part refers to the way this building can stall and restart at certain steps, held up at particular nuclei before moving on. The details are the work of specialists, and I will not pretend they are simple. But the outcome is what matters to us tonight, and the outcome is beautiful in its strangeness. This process, running only in the hottest layer just above a buried neutron star, builds up a very particular set of elements. Makes elements that ordinary stars struggle to make, or make only in small amounts, or make in different proportions. In particular, it is expected to produce an excess of certain heavier elements, elements with names you may half remember from a chemistry class long ago. Rubidium, strontium, yttrium, zirconium, molybdenum. And alongside these, an unusual overabundance of one of the lightest elements of all, lithium, which ordinary stars tend to destroy rather than make. So the burning near the dead heart leaves a signature, a particular recipe of elements, an odd mix that should not be there in a normal red supergiant. And this is the crucial thing, the thing that turns a hidden creature into something we might actually find. Because everything else about a Thorne-Zytkow object is buried. The neutron star is at the center, invisible. The strange engine runs deep down, out of sight. From the outside, as we have said, the object looks like an ordinary red supergiant, and no telescope can ever peer down to its core. The elements made by that strange burning do not stay at the bottom. In the heavier objects, the whole envelope churns and turns over, like a pot of soup at a slow boil, carrying material up from the deep hot layers all the way to the surface. And so the fingerprint of the buried process, that odd recipe of rubidium and molybdenum and lithium, is carried up and spread across the visible surface of the star, where, at last, can leak out into the light. The secret of the core is written into the color of the surface. The dead heart signs its name in the star's light. So here is where we have arrived. The Thorne-Zytkow object does not burn like a normal star. In its lighter form, It shines by the slow rain of its own gas falling onto the corpse at its centre. In its heavier form, it shines in part through an exotic burning near the neutron star's surface, a rapid capture of protons that builds up a strange set of elements. And that strange set of elements is the only thing about the whole creature that ever reaches us. It is the one clue, the one thread that leads back to the hidden heart. Everything else is sealed away. That the chemistry, the odd recipe in the light, is the door left ajar. And so the great question of finding one of these objects comes down to a single patient task. Can we read the light of a red supergiant carefully enough to see whether that odd recipe is written in it? Can we tell from colour alone whether a giant has a dead star at its heart? That reading, that careful decoding of starlight, is the long detective work at the centre of tonight's story, and it is where we will spend a good, slow while. Because the measuring, as I told you at the start, is half the tale. Let us learn how it is done. I want to stay a little longer with the two engines, the falling and the burning, because the way they divide between lighter and heavier objects is one of the more beautiful pieces of the whole picture, and it is worth feeling slowly rather than passing over. Think of it as two different ways for the same kind of creature to keep its light on, chosen not by any decision but simply by how much gas the giant carries in its great envelope. If the envelope is on the lighter side, holding less than about 8 times the mass of our Sun, then the creature shines mostly by the falling. Gas drifts down onto the dead heart, gains its tremendous energy in the long plunge down that bottomless well of gravity, and gives that energy back as light. The lighter creature is powered by the rain of its own body onto the corpse at its centre. It shines by feeding, drop by drop, the grave at its heart. But if the envelope is on the heavier side, holding more than roughly 14 times the mass of the Sun, then something new becomes possible, and the creature shines in a different way. Now the envelope is so massive and so hot near the bottom, and it churns so thoroughly from top to bottom, that the exotic burning we spoke of, the rapid capture of protons, can run in the searing layer just above the neutron star's surface. The heavier creature is powered not mainly by the falling, but by that strange nuclear building near the dead heart, and it is only the heavier creatures, the ones with this churning, burning envelope, that make the full strange recipe of elements and carry it up to the surface where we can read it. And I should be honest that the exact dividing line between these two behaviours is not a sharp fence but a blurred border, and it is still a matter of study. Some of the modelling suggests that the fully churning envelope, the kind that can run the strange burning and mix its products all the way to the surface, sets in somewhere above roughly 12 times the mass of the Sun. The numbers shift a little as the models improve, and I give them to you as the careful estimates they are, not as fixed and final fact. But hold the shape of it, even if the exact numbers stay soft. There are, in effect, two kinds of these creatures. The lighter ones, shining by the fall, quieter in their chemistry, harder to tell apart from ordinary stars because they may not carry the full strange recipe. And the heavier ones, shining by the strange burning, churning their exotic elements all the way up to the surface, wearing the fingerprint plainly enough that we might, with care, read it. And this matters enormously for the hunt, because it means that only the heavier creatures are really findable. Only they carry the full signature. The lighter ones, if they exist, would be nearly impossible to pick out, shining quietly by the fall, keeping their chemistry too plain to betray them. So when astronomers hunt for a Thorne-Zytkow object, they are really hunting for the heavier kind, the churning, burning kind that writes its recipe boldly enough to be read across 200,000 light-years of dark. The lighter kind may be all around us, hidden, unfindable, keeping their secret even better than their heavier cousins. We would never know. There is a strange humility in that thought. It means that even our very best hope of finding one of these creatures is a hope of finding only a certain kind of them, the loud ones, the ones that happen to sign their names where we can read them. Quiet ones would slip past us entirely. And so, whatever we find, or fail to find, the true number of these creatures in the sky may always be larger than the number we could ever catch. The universe may be quietly full of giants with dead hearts that shine too plainly to be told, apart from ordinary stars, and we would go on, none the wiser, thinking them rare, when really we simply cannot see most of them. That is the kind of honest uncertainty that sits underneath so much of what we know about the sky. We can only ever count the things that happen to be countable. The rest keep their secret, and we must hold our numbers gently, knowing they are flaws and not final tallies, the least the universe holds rather than the most. And so the recipe, that faint excess of rubidium and molybdenum and lithium, becomes even more precious than it first seemed. It is not merely the one clue that leaks out from a hidden heart. It is the one clue that leaks out from the one kind of these creatures we could ever hope to find. Everything narrows down to that faint chemical signature, written in the light of the heavier, churning, burning creatures, the only ones loud enough to be heard across the dark. That is the thread we follow. That is the whole game. A trace of strange elements in a spectrum from the one kind of dead-hearted giant that cannot quite keep its secret. Let us hold the preciousness in mind as we turn now to the reading of the light itself. Let us slow right down now, because we have come to the part of the night that rewards patience most. We have a creature that hides everything except a faint recipe of elements written into its light. And so the whole task of finding one comes down to learning how to read that light. This is the detective work. This is how we reach a heart we can never touch, using nothing but the glow that leaves the star and crosses the dark to us. I want to take it very gently, one idea at a time, because each step is a small marvel on its own. Start with the light itself. When you look up at a star, it seems to give off a single colour, a warm white or a cool blue or a soft red. That single colour is a blend, the way white light from the sun is really a blend of every colour woven together. You have seen this blend come apart. When sunlight passes through a raindrop, or through a glass prism, or through the fine mist of a garden hose, it spreads out into a band of colours, red and orange and yellow and green and blue and violet, laid side by side. That spread out band is called a spectrum, and it is simply the light of the star taken apart and laid out in order from the longest waves to the shortest, so we can see everything that was blended inside it. Astronomers do this on purpose and with great precision. They take the light of a distant star, gathered by a great telescope, and they pass it through an instrument that spreads it out into a spectrum far more finely than any prism ever could. And when they do, something wonderful appears. The band of colour is not smooth and unbroken. It is crossed by dark lines, thin gaps where certain exact colours are missing, as if someone had drawn faint pencil marks straight down through the rainbow at particular places. Those dark lines are the whole secret. Those dark lines are how we read the elements in a star. Here is why they appear, and it is one of the loveliest facts in all of science. Every element in the universe, every kind of atom, hydrogen and helium and lithium and rubidium and all the rest, absorbs light at its own exact set of colours, and no two elements share the same set. It is as if each element has its own private handful of colours. It likes to drink, and it drinks only those and no others. So when the light from deep inside a star climbs up through the star's cooler outer layers on its way out, the atoms in those layers each drink their own particular colours out of the passing light. And the colours they drink go missing from the spectrum, leaving those thin dark lines behind, each line at the exact colour that some particular element likes to absorb. So when we spread out a star's light and see a dark line at a certain colour, we can say with real confidence that a certain element is present in that star, because only that element drinks at that exact colour. And if we see many dark lines, we can name many elements. And more than that, if a line is deep and strong, it tells us there is a great deal of that element drinking heavily. And if a line is faint, it tells us there is only a little. Pattern of dark lines in a star's spectrum is, quite literally, a list of what the star is made of, written in the language of missing colours. It is a fingerprint. It is a signature. It is the star telling us its own recipe, if only we know how to read it. And now you can perhaps feel where this is going. Because a Thorne-Zytkow object, we said, has a strange recipe. That exotic burning near its dead heart makes an odd set of elements, rubidium and molybdenum and lithium and their relatives, and the churning of the envelope carries them up to the surface, where they lie in the outer layers through which the light must pass. So the atoms of those strange elements drink their own colours out of the star's light, and leave behind their own dark lines in the spectrum. The dead heart signs its name, and its name is written in those particular lines, at the particular colours that rubidium and molybdenum and lithium like to absorb. If we can find a red supergiant whose spectrum shows an unusual excess of exactly those lines, deeper and stronger than they have any right to be in an ordinary giant, then we may be looking at the fingerprint of a buried neutron star. We may be looking at a Thorne-Zytkow object. But I have to slow us down here and be honest about how hard this really is, because the difficulty is the whole reason no one has ever confirmed one of these creatures. It sounds simple when I lay it out. Spread the light, find the strange lines, name the buried heart. The sky does not make it simple. There are many ways for a star to show unusual lines, and only one of them is a dead star at the center. So the detective cannot simply see the strange elements and declare victory. The detective has to rule out every other explanation, one by one, patiently, before daring to say what the lines truly mean. And that ruling out is where most of the real work lies. Consider the first difficulty. How do you even know that a line is unusually strong? Strong compared to what? A single spectrum on its own is just a pattern of lines. To know whether the rubidium line is stronger than it should be, you need to know how strong it would be in an ordinary red supergiant, one with no dead heart, just a normal burning core. And so the search for a Thorne-Zytkow object cannot ever be the study of one star alone. It must always be a comparison. You have to take your suspect, the strange giant you are curious about, and you have to place its spectrum beside the spectra of many ordinary red supergiants, as many as you can gather, all of them normal, all of them well understood. And only by holding your suspect up against that crowd of ordinary giants can you see whether its lines truly stand out, whether its rubidium and its molybdenum and its lithium are genuinely in excess, or whether they only seemed strange because you had nothing to compare them to. This is a quiet but important truth about how we come to know the sky. We almost never learn anything from a single object in isolation. We learn by comparison, by gathering the ordinary many so that the extraordinary one can reveal itself against them. The strangeness of a suspect star only becomes visible when it is set against a great crowd of its ordinary cousins. So the astronomer hunting for a dead heart is really building two things at once. A careful portrait of the suspect and a careful portrait of what normal looks like, so that any difference between them can be trusted. It is slow. It is painstaking. It is the opposite of a single dramatic glimpse. It is the long, patient accumulation of comparison. And there is a good reason to gather all those ordinary giants from the same neighborhood of the sky as the suspect, ideally from the very same galaxy. Because stars that live together tend to be made from the same batch of raw material, born from the same great cloud, sharing the same starting recipe. If you compared your suspect to ordinary giants from some far-off and different place, you might be fooled by differences that have nothing to do with a dead heart and everything to do with the two stars simply having been born from different clouds. So the careful hunter gathers a crowd of ordinary red supergiants from the same galaxy as the suspect, born from the same material, and asks only then whether the suspect stands apart. This is one of the reasons the search has focused on certain nearby galaxies where many red supergiants can be studied together, side by side, under the same conditions. We will come to the particular galaxy where the best candidate was found. But first there is another difficulty to face, and it is a subtle and beautiful one, and it has to do with whether the suspect is even truly where we think it is. Here is the difficulty, and it is the kind of thing that only troubles you once you realize the sky is not flat. When you look up at the night, everything seems to sit on the same great dome, as if the stars were all pinned to the inside of a dark bowl turned over your head. But of course they are not. Some are near and some are unthinkably far, and yet from where we stand, a near star and a far star can appear in almost exactly the same spot, one behind the other, lined up by pure chance along your line of sight. You cannot tell just by looking which is close and which is distant. They both sit on the dome. They both are only points of light. Now think about what that means for our detective. Suppose you find a red supergiant with a strange spectrum sitting in the direction of a distant galaxy, and you get excited, because a strange giant in a distant galaxy is exactly the sort of place a Thorne-Zytkow object might live. But how do you know the giant is truly in that distant galaxy at all? How do you know it is not, instead, a much nearer star, one that belongs to our own galaxy, sitting in the foreground, that just happens to fall along the same line of sight as the far-off galaxy behind it? From where you stand, the two look the same. A member of the distant galaxy and a nearer foreground star pretending to be one would sit in the very same spot on the dome. And this matters enormously because a star's true nature depends on its true distance. A giant that is genuinely far away in another galaxy must be tremendously bright to appear as bright as it does. But a foreground star that is actually much closer could be a far more modest object, only appearing prominent because it is near. The strange lines might mean one thing if the star is a distant supergiant, and something quite ordinary if it is a nearer star of a different kind entirely. So the detective faces a real problem. Before you can say what a suspect is, you have to know where it is. And knowing where it is, knowing its true distance, is one of the oldest and hardest challenges in all of astronomy. So let us step back, as we so often must, and spend a while on the beautiful old art of measuring how far away a star lies. Because this, too, is part of reaching a hidden heart with only starlight. Oldest and surest method is a trick you can play with your own eyes right now, tonight, wherever you are lying. Hold up one finger at arm's length and look at it first with only your left eye, then with only your right, closing one and then the other. Watch how your finger seems to jump back and forth against the far wall behind it, even though your finger has not moved at all. It jumps because your two eyes look at it from slightly different places, and each eye sees it against a slightly different background. That apparent jump is called parallax, and the closer your finger is to your face, the bigger the jump. Move your finger far away, and the jump grows small. Hold something across the room, and it barely jumps at all. Astronomers use this very same trick to measure the distances to nearer stars, only that two eyes are not the two sides of a face. Their two eyes are the two opposite sides of the Earth's great orbit around the Sun. As our planet travels its long yearly path, we see the nearer stars from one side of that orbit in one season, and from the far opposite side half a year later, from a vantage point tens of millions of miles away from the first. And against the distant background of much farther stars, the nearer stars seem to shift ever so slightly back and forth over the course of the year, just as your finger shifts when you blink from eye to eye. The nearer the star, the larger the shift. The farther the star, the smaller. And by measuring that tiny yearly shift with great care, astronomers can work out how far away a star truly lies. It is the same simple geometry as your finger and your two eyes, only stretched across the width of a planet's orbit and applied to the depths of the sky. But there is a catch, and it is the catch that makes distance so hard. The farther away a star is, the smaller its parallax shift becomes, until, for truly distant stars, the shift grows so tiny that it slips below what we can measure at all. For stars in another galaxy, hundreds of thousands of light years away, the yearly shift is far too small to see by this method. The finger has been carried so far away that it no longer seems to jump at all, no matter how carefully you blink. So parallax, wonderful as it is, only reaches so far. Measures the nearest stars beautifully, and then it runs out. And that is exactly why the foreground problem is so troublesome. The very method that could tell a near star from a far one works best on the near ones and fades just where we need it most. And yet parallax and its close cousin can still help us in a crucial way, even when we cannot measure the full distance to a faraway galaxy. Because there is another thing we can watch besides the yearly back and forth shift, and that is the star's own slow drift across the sky over the years. Every star is moving through space, and as it moves, it slowly changes its position against the far background, creeping across the dome year by a tiny amount. This slow creep is called proper motion, and it is the star's true travel across our line of sight, not the yearly wobble of parallax, but a steady one-way drift. And here is the clever thing. Nearby stars, the foreground stars in our own galaxy, drift noticeably across the sky over the years because they are close, and closer things appear to move faster, just as a nearby bird crosses your view quickly while a distant airplane seems to hang almost still. But a star in a distant galaxy, hundreds of thousands of light years away, is so far off that its drift across the sky is almost nothing, far too small to notice, no matter how fast it may truly be travelling through space. So if you watch a suspect star patiently and measure its drift, you can tell a great deal about whether it is near or far. A large drift betrays a nearby foreground star, an imposter. A drift so small it can barely be measured is the mark of a truly distant object, a genuine member of the far-off galaxy. This is where one of the great instruments of our age enters the story, and I want to give it its due, because it changed everything about this kind of question. There is a spacecraft called Gaia, launched to sit far from the Earth and do one thing with almost unbelievable precision: measure the positions, the distances, and the motions of more than 1 billion stars. Gaia watches the sky year after year, tracking the tiny yearly wobble of parallax and the slow, steady creep of proper motion for star after star after star, building the most precise map of the heavens that has ever existed. Measures shift so small they are like watching a coin turn edge on from across a continent. And with a map like that, the foreground problem, which had troubled astronomers for so long, could at last be attacked directly. For a suspect star, you could ask Gaia plainly, how much does this star drift across the sky? And from the answer, you could tell whether it truly belonged to the distant galaxy, or whether it was only a nearer star wearing the galaxy as a backdrop. So now we have gathered our tools, and I want to lay them out together before we go to the one star that has come closest to being the real thing, because the tools are the true heart of this hunt. We can spread a star's light into a spectrum and read its elements from the dark lines. We can compare a suspect against a crowd of ordinary red supergiants from the same galaxy to see whether its strange elements truly stand out. And we can measure the suspect's drift across the sky with the help of a spacecraft built for exactly that, to be sure it lives where we think it lives and is not a nearer star lined up by chance. 3 tools: the rainbow, the crowd, and the drift. And with those 3, and years of patience, we can reach toward a heart no telescope can ever see into. Now let us meet the star that brought all 3 tools to bear and became, for a while, the best hope anyone had ever had of finding a dead heart inside a living giant. Before we go to the candidate itself, I want to linger on one more piece of the detective work, because it explains why the search has gone hunting in certain galaxies rather than simply staring at the stars nearest to us. And it is a quietly clever piece of reasoning, the kind worth turning over slowly in the dark. You might think the best place to look for a red giant with a dead heart would be close to home, among the stars of our own galaxy, where everything is nearest and brightest and easiest to study. There is a problem with looking close to home, and it is a problem of the crowd, though a different crowd than the one that captures neutron stars in clusters. When you look for red supergiants within our own galaxy, they are scattered all across the sky at all sorts of different distances, near and far, jumbled together. And because they lie at so many different distances, it is hard to compare them fairly. One might look bright only because it is near. Another might look faint only because it is far. And to make it worse, our galaxy is full of dust, great dark clouds of it drifting between the stars, dimming and reddening the light of anything behind them, so that a star's true colour and true brightness are muddied by whatever gas and dust happen to lie along the way. Studying red supergiants in our own galaxy is like trying to compare the heights of people scattered across a hilly, foggy landscape, some near and some far, some behind trees, some in shadow. Can be done, but it is hard to do fairly. Now consider instead a nearby companion galaxy, like the Small Magellanic Cloud, or its slightly larger sister, the Large Magellanic Cloud. When you look at one of these, you are looking at a whole galaxy's worth of stars, all gathered, more or less, at the same distance from you, off in the same direction, like a crowd of people standing together on a distant hillside rather than scattered through the fog. Every red supergiant in that galaxy is about 200,000 light-years away, give or take. So when you compare them, you are comparing them fairly, because they all lie at nearly the same distance, and a difference in how bright they look really does mean a difference in how bright they truly are. You can gather them all together, all the red supergiants of that one galaxy, and lay their spectra side by side and ask cleanly which of them stands out. The far hillside, oddly enough, is easier to study than the foggy ground at your feet, precisely because everyone on it is standing at the same distance. And there is another reason these companion galaxies make good hunting grounds, and it has to do with what they are made of. The Small Magellanic Cloud is what astronomers call metal poor, which is their particular way of saying that it holds fewer of the heavier elements than our own galaxy does. Now, remember that the whole signature of a Thorne-Zytkow object is an excess of certain heavier elements, rubidium and molybdenum and lithium and the rest, made in that strange burning near the dead heart. If you are looking for a star with an unusual excess of those elements, it helps to look in a place where the background level of them is low to begin with. Ordinary stars are not already rich in such things. Against a metal-poor background, a star that is genuinely enriched by the strange burning stands out more clearly, like a bright mark on a pale page, rather than a bright mark on an already busy one. So a metal-poor companion galaxy is, in two ways at once, an ideal place to hunt. Everything is at the same distance, so comparisons are fair. And the background is clean, so a true excess is easier to spot. This is the kind of careful thinking that goes into a search you never see, the reasoning that happens long before any telescope is pointed anywhere. Where should we even look? Which galaxy gives us the fairest comparison and the cleanest background? How do we gather enough ordinary red supergiants to know what normal looks like, so that the extraordinary one can reveal itself against them? These questions are answered on paper, in careful argument, before a single night of observing begins. And the answer, for much of this hunt, was to look toward those nearby companion galaxies, the Magellanic Clouds, where whole populations of red supergiants could be studied together fairly, against a clean background all at once. It was in exactly such a search through the red supergiants of the Small Magellanic Cloud that the best candidate was found. Not by chance. By staring at a random star, but by carefully deciding where to look and then looking patiently, star after star after star, until one of them stood out from all its ordinary cousins. Let us go now to that one. The story of the best candidate begins with a galaxy you can almost see with your own eyes, if you live far enough south and far enough from the glow of any city. Down low in the southern sky there hangs a soft, dim smudge of light, like a small torn piece of the Milky Way that has drifted away on its own. It is called the Small Magellanic Cloud, and it is not part of our galaxy at all. It is a whole separate galaxy, a small companion to our own, wheeling slowly around the Milky Way out in the dark. It is one of our nearest neighbours among all the galaxies, and it holds within it many hundreds of millions of stars, its own crowd of suns, its own red giants, its own quiet dramas playing out far beyond our reach. And it is far. The Small Magellanic Cloud lies about 200,000 light-years away from us. I want to let that number rest in the air for a moment, because it is one of the anchors we will return to tonight, and it deserves to be felt rather than merely heard. A light-year is the distance light travels in a single year, and light is the fastest thing there is, crossing the space between the Earth and the Moon in about a second. In 1 year, light travels a distance so vast that laying it out in miles would give a number too long to hold in the mind. And the Small Magellanic Cloud is 200,000 of those lengths away. So think about what that means for the light itself. The light you might gather from a star in that little galaxy tonight did not leave it recently. It left about 200,000 years ago. It has been travelling across the dark all that time at the greatest speed the universe allows, and it is only now arriving. 200,000 years ago, there were no cities, no farms, no written words, no history at all as we would know it. The first modern humans were only beginning to walk the earth. And in that same ancient moment, a beam of light left a star in a small companion galaxy and set out across the void, and has been falling toward us ever since, through the entire span of everything our kind has ever done, only to end its long journey now, gathered into a telescope, spread into a spectrum, and read. When you look at the light of that galaxy, you are not seeing it as it is. You are seeing it as it was before your people had a single story to tell. The past is the only thing the sky ever shows us. It was in that far and ancient galaxy that astronomers found their best candidate. In the year 2014, a team of astronomers announced that a particular star in the Small Magellanic Cloud, a star with the plain catalogue name of HV 2112, might be the first Thorne-Zytkow object ever found. The team was led by an astronomer named Emily Levesque, and among those working alongside her were Massey and Nidia Morrell, and, movingly, Zytkow herself, one of the two people who had first dreamed the creature into being nearly 40 years before. She had helped imagine it as a young astronomer. Now, decades on, her name was on the paper pointing to the best example anyone had ever found. There is a whole human life folded into that fact, a patience measured not in years but in careers, a question carried faithfully from youth into age. They had gathered the light of HV 2112 using one of the great telescopes of the southern hemisphere, a giant instrument high in the clear dry air of the mountains of Chile, at a place called Las Campanas, where the skies are among the darkest and steadiest on Earth. It was one of a pair of enormous telescopes there, each with a mirror more than 20 feet across, a great curved eye of glass gathering the faint ancient light of a star 200,000 light years away, and pouring it into an instrument that could spread it into its colours. That is what it takes to read the recipe of a single star in another galaxy. a mirror wider than a room, on a mountain top, drinking in light that set out before human history began. And when they spread that light into a spectrum and read its dark lines, they found something that made their hearts quicken. The lines of certain elements stood out, stronger than they should be in an ordinary red supergiant. There was an excess of rubidium. There was an excess of molybdenum. There was an excess of lithium. And there were signs of other unusual elements as well, including calcium. These were, near enough, exactly the elements that the theory had predicted all those years before that a Thorne-Zytkow object should make in that strange burning near its dead heart and should carry up to its surface for us to see. The recipe in the light seemed to match the recipe on the page. The fingerprints seemed to fit. Here was a red supergiant in a nearby galaxy wearing in its light the very signature that a buried neutron star was supposed to leave behind. It was, they said, the best candidate ever found. I want to dwell on how that must have felt, because moments like it are rare in a scientific life. For nearly 40 years, the Thorne-Zytkow object had lived only in theory, a creature drawn from equations, a should and a could, with no example anywhere in the sky. Astronomers had looked and found nothing certain. And now, at last, here was a star that seemed to carry the mark. To read those lines and to see the predicted elements standing out just as the theory said they would must have felt like meeting, in the flesh, a creature you had only ever known from an old and careful drawing. Portraits sketched from physics alone decades before seemed finally to have found its living match. But I have to be very careful now, and I have to slow us down, because this is the exact point where the story turns from triumph to something more honest and more interesting. And it is the point that matters most, so I will not rush it. Because a candidate is not a confirmation. The word candidate carries within it all the doubt that the word discovery would throw away. And the case of H52112, best candidate though it was, did not settle into certainty. It opened, instead, into a long and careful argument, the kind of argument that is not a failure of science, but its very engine. Other astronomers looked at the same star and the same light and began to ask hard questions. Was the recipe truly as strange as it seemed? Was the star even where they thought it was? Could there be another, more ordinary explanation for everything they had seen? And those questions, asked patiently over the following years, are where the real texture of this science lives. Let us follow them, one at a time, because the doubt is as beautiful as the hope and far more instructive. The first hard question came from the recipe itself, and it was this. Was the strange mix of elements in HV2112 truly the signature of the buried neutron star, or could an ordinary kind of star, living out an unusual old age, make something that looked almost the same? Because the universe, it turns out, has more than one way to build a strange giant. There is a rare and interesting sort of star called a superasymptotic giant branch star, and the name is a mouthful, so let us just think of it as a very massive dying giant, near the upper edge of the stars that end their lives quietly rather than in a great collapse. These stars, in their final stages, churn and dredge up material from deep within themselves, and they can pour unusual elements up to their surfaces too, including some of the very same elements that a Thorne-Zytkow object is supposed to make. And so, not long after the candidate was announced, other astronomers pointed out that HV 2112 might not be a star with a dead heart at all. Might instead be one of these massive dying giants, an unusual but entirely ordinary late-life star, making its strange elements by its own ordinary means, with no neutron star buried anywhere inside it. Two possibilities could look remarkably alike from the outside, in the pattern of their lines, and telling them apart would take more than a single spectrum. I want you to notice how deflating and how healthy that is at the same time. Deflating because it means the best candidate might be nothing special at all, just an unusual old giant of a well-understood kind. And healthy because this is exactly what science is supposed to do. Does not fall in love with its most exciting answer. It asks coldly and fairly whether a duller answer would fit the same fact. And if the duller answer fits, it cannot be ruled out just because it is less thrilling. So the field was left with two live possibilities side by side. A dead heart or an ordinary old giant. And no clean way yet to choose between them. Then came a second hard question, and this one struck at something even more basic. Was H52112 even in the Small Magellanic Cloud at all? Remember the foreground problem, the trouble of near stars and far stars lining up by chance along the same line of sight. A group of astronomers looked at how the star drifted across the sky, its proper motion, that slow creep we spoke of, and they found what seemed to be a rather large drift, larger than you would expect from a genuine member of a galaxy 200,000 light-years away. And from that, they argued that HV 2112 might not be a distant supergiant in the Small Magellanic Cloud at all. Might instead be a much nearer star, one belonging to our own Milky Way, sitting in the foreground, of a particular kind called an S-star, only appearing to sit within the distant galaxy by the accident of alignment. If that were true, then the whole case would collapse, because a nearer, more modest star would not need any exotic explanation for its light. The strange recipe might mean nothing at all. So now there were not two questions, but a tangle of. Was it a dead heart, or an ordinary dying giant? And was it even in the galaxy we thought, or a nearer imposter? And here is where the great mapping spacecraft, Gaia, entered the story and did what it was built to do. Gaia had measured the drift of so many stars, so precisely that astronomers could go back to HV 2112 and check its motion against the finest map ever made. And when they did, using Gaia's data, they found that the earlier worry did not hold up. The star's drift across the sky was, in fact, small enough to be consistent with a genuine member of the Small Magellanic Cloud after all. The foreground worry faded. By around the year 2018, the evidence from Gaia pointed to HV 2112 truly sitting where it had first been placed, out in that distant companion galaxy, a real supergiant 200,000 light-years away, and not a nearer imposter at all. One of the doubts had been answered. The star was where they thought. Answering one doubt is not the same as ending the argument, and the recipe question remained. So astronomers went back to the light of HV 2112 again, this time with another of the great telescopes of the south, an enormous instrument known as the Very Large Telescope, and they read its spectrum once more, even more carefully than before. And what they found was a mixed and honest result, the kind that does not close a case but sharpens it. The unusual amount of lithium they found seemed to hold up. That part of the strange recipe still appeared to be there. But the excesses of some of the other elements, including the rubidium and the calcium that had been part of the original excitement, now looked less certain. Some of the numbers that had made the first case so compelling did not stand as firmly on a second, harder look. So the picture became more tangled, not less. Part of the fingerprint survived. Part of it grew doubtful. And a star that had seemed for a while to match the theory almost perfectly now matched it only in part, with real questions hanging over the rest. And it did not stop there, because good science rarely stops at a single object. Astronomers went looking for other candidates too, other red supergiants that might wear the same mark. Another star, with the catalogue name H5 11417, was studied as a further possible Thorne-Zytkow object, another suspect to weigh against the theory. The search widened, as searchers do, from one star to a small handful, each one examined, each one debated, none of them settling the matter beyond doubt. So let me now say plainly where all of this leaves us, because the honest state of the field is the most important thing I can give you tonight, and I want to say it clearly and more than once. No Thorne-Zytkow object has ever been confirmed. Not one. The entire class of these creatures remains, to this day, a prediction of physics rather than a proven fact of the sky. The theory is strong and beautiful and self-consistent. Candidates are real and tantalizing. There is not, as of now, a single star anywhere that astronomers can point to and say with full confidence that one, beyond argument, is a giant with a dead heart. H5 2112 is a candidate, not a verified case. It may be a Thorne-Zytkow object. It may be a super-asymptotic giant branch star, an unusual but ordinary dying giant. The evidence has swung back and forth, some worries laid to rest, others raised, and the case remains open. And I want to be just as clear about the formation stories, the two roads we walked earlier. The slow spiral of a neutron star through the common envelope of its swelling partner, and the capture of a lone corpse in the crowded heart of a cluster. Both of these are models. Both are reasoned out from the laws of physics and built up in simulations. Neither is an eyewitness account. No one has watched a neutron star sink into the heart of a giant. When we speak of how these objects form, we are speaking of what should happen and what could happen according to our best understanding, and never of what anyone has actually seen happen. Every would in this story, every should, every might, is doing honest work. They are not weak words. They are the true words. They mark the exact line between what we have reasoned and what we have witnessed, and that line is where all real science lives. I find there is something restful rather than disappointing in holding it this way. We do not need the creature to be confirmed for it to be worth our wonder tonight. It is enough that the laws of nature allow such a thing. It is enough that somewhere, perhaps, a giant is glowing with a dead heart at its center, and that we have reasoned our way to the very edge of being able to find it, and stand there now, patient, uncertain, still looking. The not knowing is not a failure. It is the honest shape of a mind reaching towards something just past the limit of its sight. Let us go back, for a while, to the patient art of measuring, because there is more to it than reading the dark lines, and the more you understand of how we weigh and size a star we can never visit, the more astonishing it becomes that we can say anything about these creatures at all. I told you earlier that the measuring is half the story, and I meant it. So let us sit a while longer with the question of how you come to know a star's true size, its true brightness, and even, in a way, its weight, when all you will ever have of it is a thread of light. Begin with color, because color tells us heat. You already know this from the world around you, even if you have never named it. When a piece of metal is warmed in a fire, it first glows a dull red, and then, as it grows hotter, it brightens to orange and then to yellow, and if it could be made hotter still without melting away, it would glow white and then even a faint blue. Color of a glowing thing tells you its temperature. Cooler things glow red. Hotter things glow blue. And stars obey the same rule exactly. A red star is a cool star, as stars go, with a surface far gentler than the blaze of a blue one. A blue star is a fierce, hot star. And a yellow star, like our sun, sits somewhere in between, comfortable and middling. So when we see that a red supergiant glows deep red, we already know something true about it. Its surface is cool, cooler than the surface of our sun, which is part of why these giants can grow so vast and still hold together. They have spread their light and their heat across an enormous surface, and so any single patch of that surface is not so very hot. The redness is the sign of that coolness. And by measuring the exact shade of the light, by seeing precisely how the brightness is spread across the colors of the spectrum, astronomers can read the surface temperature of a star with real precision, not by guessing, but by matching the shape of its glow to the known behavior of hot and cool things. Is a thermometer held up to a star from across the dark? Now put color together with brightness, and something wonderful becomes possible. Suppose you know how hot a star's surface is from its color. And suppose you also know how far away the star is, so that you can work out its true brightness, how much light it truly pours out. not merely how bright it happens to look from here. Candle nearby and a bonfire far away can look equally bright to your eye, and only by knowing the distance can you tell the modest flame from the great blaze. So distance turns apparent brightness into true brightness. And once you know a star's true brightness and its surface temperature together, you can work out how large it must be. Because a hot surface pours out a great deal of light from every small patch of itself, while a cool surface pours out only a little from each patch. So if a star is cool at the surface, glowing gently red, and yet it is tremendously bright overall, pouring out far more light than any small star could, then it must be enormous. It must have a vast surface, a huge area of gently glowing gas to add up all those faint patches into so great a total. The only way to be both cool and brilliant is to be huge. And that is exactly how we know that red supergiants are as large as they are. Not by measuring their width directly, for most of them are far too distant to show any width at all, but by reasoning from their colour and their brightness together. Cool, and yet blindingly luminous, therefore vast. It is a chain of careful thought, each link tested, reaching all the way out to the true size of a star we see only as a point. And you can perhaps feel now why the distance to the Small Magellanic Cloud mattered so much in the story of our candidate. Every one of these judgments, the true brightness, the true size, depends on knowing how far away the star lies. The distance wrong, and the star's whole nature shifts beneath your feet. Place it too near, and it becomes a modest object needing no exotic explanation. Place it truly far, out in that distant galaxy, and it must be tremendously luminous, tremendously large, exactly the sort of giant that could hide a dead heart. So the argument about whether HV 2112 was a distant supergiant or a nearer imposter was never a small technical quibble. It was an argument about the star's entire nature, resting on that single number, its distance. This is why astronomers labour so hard over distance, why the mapping spacecraft mattered so much, why the drift across the sky was studied so carefully. Distance is the foundation stone. Get it wrong, and everything built upon it leans and falls. And how do we know the distance to a whole galaxy like the Small Magellanic Cloud in the first place, when parallax, the finger and two eyes trick, cannot reach so far? Here, the astronomers use another beautiful tool, a special kind of star that acts as a measuring stick across the void. There are stars called Cepheid variables which have a remarkable and dependable habit. They pulse. They brighten and dim in a slow, steady rhythm, swelling and shrinking like a great slow heart. And more than a century ago, an astronomer named Henrietta Leavitt discovered something extraordinary about these pulsing stars. The rhythm of their pulsing is tied directly to their true brightness. A Cepheid that pulses slowly is truly very bright, and one that pulses quickly is more modest, and the relationship is so dependable that if you simply watch how long a Cepheid takes to complete its cycle, you can know how much light it truly pours out. And once you know a star's true brightness, its distance falls out of the comparison with how bright it merely appears. A Cepheid that should be blazing, yet looks faint to us, must be very far away, and exactly how faint it looks tells you exactly how far. So these pulsing stars became a kind of ruler laid across space. Find a Cepheid in a distant group of stars, watch its rhythm, learn its true brightness, compare it to how faint it looks, and you have the distance to the whole group. The Small Magellanic Cloud, as it happens, was one of the very places where this method was first worked out, where Henrietta Leavitt studied her pulsing stars, and it is in part through such stars that we know its distance of about 200,000 light-years as well as we do. There is a lovely circle in that. The very galaxy that holds our best candidate is also one of the galaxies that first taught us how to measure the distances to galaxies at all. So we have colour for heat, and brightness with distance for true size, and pulsing stars for the distances themselves. And there is one more thing I want to add to our understanding of these giants before we go on, because it explains the single most important step in how a dead heart ever reveals itself. And that is the matter of churning, of how the inside of a great giant mixes itself. In a calm, small star, the layers can be rather still, with heat carried up gently and little mixing between the deep interior and the surface. But in a great red supergiant, and especially in the heavier Thorne-Zytkow objects, the outer envelope does not sit still at all. It churns, boils. Great columns of hot gas rise up from the deep interior toward the surface, and cooler gas sinks back down in enormous slow currents that turn the whole envelope over and over, the way water turns over in a heated pot, or the way the air rises in great cells over a warm field on a summer day. Astronomers call this convection, and it is simply the carrying of heat by the bodily rising and sinking of gas, rather than by light alone. And convection is the reason the dead heart can ever be found. Because the strange elements, remember, are made deep down, in that searing layer near the neutron star, far below the surface, in a place no light from outside could ever reach. If the envelope sat still, those elements would stay trapped at the bottom, sealed away forever, and no fingerprint would ever appear in the star's light. But the envelope does not sit still. It churns from top to bottom. And so the strange elements made in the depths are caught up in the great rising currents and carried all the way to the surface, where they spread out into the outer layers, into the very gas through which the light must pass on its way to us. The churning is what lifts the secret from the grave to the surface. Without it, the recipe would never leak out, and these creatures, if they exist, would keep their nature entirely to themselves, hidden past any hope of finding. It is only because a great giant boils all the way through that the dead heart can sign its name in the light at all. The mixing is the messenger. Churning carries the message up from the depths and hands it to the light, and the light carries it across 200,000 years of dark to a telescope on a mountain, to a spectrum spread into its colours, to us. Now let us sit for a while with the numbers themselves, because the scale of this creature is the truest source of its wonder, and the calm way to feel a number too large to grasp is to turn it over slowly many times in different lights. So let us turn these over together, one after another, and let each one settle before we reach for the next. Begin again with the density of the dead heart, because it is the number that undoes the imagination most gently. The neutron star packs more than the whole mass of our sun into a ball only about 12 to 15 miles across. We said earlier that a sugar cube of its matter would weigh as much as a mountain. Let us stay with that a moment longer. Not a cube the size of a house. Not a cube the size of a car. Cube the size of the little white lump you might stir into a cup of tea. And yet inside that tiny cube is packed the weight of a whole mountain, kind of mountain that takes half a day to climb and stands white-capped against the sky. Every small spoonful of the dead heart carries a mountain's worth of weight. And there is not one spoonful of it but a whole ball 12 miles across, made of that same impossible stuff, all of it, from surface to center. The mind simply cannot hold it, and that is all right. You are not meant to hold it. You are meant to feel it slip past the edges of what you can hold, and to rest in the awe of that slipping. Now set that density against the emptiness that surrounds it, because the contrast is where the strangeness truly lives. Above the dead heart stretches the great envelope of the giant, hundreds of millions of miles of glowing gas, and that gas, we said, is thinner than the air in your room, thinner in many places than the best vacuum we can make in a laboratory here on Earth. So you have, in a single object, the densest matter the universe knows how to build, wrapped inside some of the thinnest. The heaviest thing imaginable, cradled in the lightest. If you could journey inward from the surface of such a giant, you would begin in a haze so faint you could scarcely tell it from empty space, and you would fall inward for hundreds of millions of miles through gas that grew slowly thicker and hotter, and only at the very end, at the center, would you reach the crushing ball of the dead heart, where a single spoonful outweighs a mountain. The whole vast body is almost nothing, wrapped around a center that is almost everything. That is the shape of it. Emptiness around a stone of impossible weight. Now the size. We said the outer envelope of such a giant could be hundreds of times wider than the sun, wide enough that if it sat where the sun sits, its surface would reach out past the Earth and swallow the orbit of Mars. Let me lay that out slowly, in the order of the worlds. First, the star's surface would swallow Mercury, the little scorched world nearest the sun. Then Venus, wrapped in its thick, bright clouds. Then the Earth itself, the whole of it, every ocean and every mountain and every place any person has ever stood, all of it inside the star. And then it would reach past even the Earth and swallow the orbit of Mars, the red world beyond us. The entire inner solar system, all the ground of all our history and all our dreams, would fit inside this single star with room to spare. And at the very center of all that, smaller than a single grain of sand set down in the middle of that vast glowing sphere, would sit the neutron star, the dead heart, the corpse, weighing more than everything around it. try to hold both ends of that at once. A star wide enough to drown the inner solar system, and a heart smaller than a city, heavier than the whole star it hides in. That is a Thorne-Zytkow object. That is what the laws of physics say the universe is allowed to build. And now a number of a different kind, a number about how rare these creatures are, if they exist at all. When astronomers work out from the theory how many Thorne-Zytkow objects might be present in our entire galaxy at any one time, they arrive at a small figure, somewhere between about 20 and 200 of them in the whole of the Milky Way among its hundreds of billions of stars. Let that proportion settle over you. Hundreds of billions of stars wheeling through our galaxy, and among all of them, perhaps only a few dozen, perhaps a couple of hundred, that carry a dead heart. They would be needles in the greatest haystack there is, and they would not stand out. Each one would look, to a careless glance, like just another red supergiant, one more red lantern among the many, giving away its secret only in the faintest tracing of unusual elements in its light. So even if the universe does make these things, finding one would be like walking through a crowd of 100 billion people and trying to pick out the few dozen who carry, hidden and silent within them, something no one else carries. No wonder the search has been so long. No wonder no example has yet been confirmed. The wonder is not that we have not found one for certain. The wonder is that we have come as close as we have, that we can even name a candidate, that we can point to a star 200,000 light years away and say, perhaps that one. And there is a reason they would be so rare, beyond the difficulty of making them. It is that they would not last very long, as stars measure time. A Thorne-Zytkow object, if it forms, is not a stable and permanent kind of star that can shine steadily for billions of years the way our sun does. It is an unusual and precarious arrangement, and the models suggest it would endure only for a relatively short stretch of cosmic time before it changed again, before the neutron star at its center grew and shifted the balance, or the envelope was lost, or the whole strange marriage came undone in one way or another. So even the ones that do form would shine as Thorne-Zytkow objects only for a brief window in the long life of the sky, and then pass on into whatever they become next. Rare to make and brief to last. Two reasons working together to keep them almost entirely hidden from us. A creature that is hard to build and quick to change is a creature you will almost never catch in the act of being itself. I want to gather all of these numbers into one image now and hold it still, because I think it is a good thing to fall toward as the night deepens. Somewhere out in the dark, a red supergiant so vast it could drown the inner solar system, glowing a deep and gentle red, cool at its enormous surface, calm and slow and ancient. Buried at its very center, hidden past all seeing, a ball of crushed matter only 12 miles across, denser than anything you will ever touch, holding within it the weight of a whole sun, corpse of a star that died long ago. Picture the great envelope churning slowly around that corpse, boiling from its searing depths to its faint cool surface, carrying up from the grave a faint recipe of strange elements, rubidium and molybdenum and lithium, and writing that recipe into the light that leaves the star. And picture that light setting out across 200,000 years of dark, arriving at last at a great glass eye on a mountain top, spread into its colours, read by patient people who have wondered about such a creature for the length of the human life. That is the whole thing held in one still image. A dead heart, a living giant, a faint signature in the light, and a mind reaching across the dark to read it. Let that be the picture you carry now as we begin to turn slowly from what this creature is toward what it might mean for the sky and for us, small and warm and wandering here beneath it all. There is one question at the very center of tonight's wondering that I have circled but not yet faced head-on, and now is the time to face it, gently. How could we ever truly tell such a monster apart from an ordinary giant? Because this, in the end, is the whole difficulty. It is not enough to find a red supergiant with some unusual elements in its light. The universe has more than one way to make unusual elements, and the honest detective has to separate the one explanation that thrills from the several that do not. So let us walk slowly through just how fine that separation has to be. Remember the rival explanation, the massive dying giant, the one whose full name is such a mouthful that can dredge up strange elements from its own depths by ordinary means. The trouble is that this ordinary giant and the extraordinary Thorne-Zytkow object do not merely look a little alike. They can look very much alike, both of them cool and red and vast, both of them showing an excess of some of the same elements, both of them sitting at roughly the same great brightness. Nature has, in a sense, provided a decoy, a perfectly natural kind of star that mimics the signature we are hunting for. And a decoy that good means that no single clue can ever settle the matter. You cannot simply see the lithium and declare a dead heart, because a dying giant can make lithium too. You cannot simply see the rubidium, because there are ways for that to appear as well. Proof, if it ever comes, will not be one line in one spectrum. It will be a whole pattern, a full recipe, matched carefully against what only a buried neutron star should produce and what an ordinary giant should not, with every element weighed and every alternative ruled out. And measuring that recipe is itself far harder than I have let on. When astronomers read the strength of a dark line and try to turn it into an amount, a true measure of how much of an element is present, they cannot do it by the line alone. They have to build, in effect, a model of the whole outer atmosphere of the star, a careful understanding of how hot it is at each depth, how the gas is arranged, how light passes through it, so that they can work out how much of an element it would take to make a line of exactly that strength. And a red supergiant has one of the most difficult atmospheres of all to model. It is cool, which means the gas can form molecules, not just single atoms, and molecules make their own thick forests of dark lines that crowd together and overlap and half hide the lines the astronomer is trying to measure. Churns, which means it is never quite still or simple. And it is enormous and diffuse, which makes its outer layers hard to pin down. So reading the true amount of rubidium or lithium in such a star is not like reading a number off a dial. It is a careful, contested act of interpretation, dependent on the model of the atmosphere you bring to it, and two careful astronomers with slightly different models can arrive at somewhat different amounts from the very same light. This is part of why the case of our candidate swung back and forth, why the rubidium looked certain to one team and doubtful to another. They were not careless. They were reading a genuinely difficult text, in a difficult light, and honest readers can differ over a difficult text. So what, in the end, would it take to be sure? What would turn a candidate into a confirmation? It would take, most likely, not one star, but many. It would take a whole small population of these objects, found and studied together, all showing the same full pattern of strange elements, the same recipe repeated from star to star, so that it could no longer be dismissed as a quirk of one unusual giant. It would take the pattern to match, in detail, not just in one or two elements, but across the whole predicted recipe. The theory says a buried neutron star should make, and what no ordinary giant should. And it might take, someday, some entirely new kind of evidence that we have not yet learned to gather, some signal from the dead heart itself that leaks out in a way we have not thought to look for. Science has a long habit of finding new windows onto old questions. The mapping spacecraft that settled the distance question did not exist when the creature was first dreamed up. The great telescopes that read these faint spectra were beyond imagining when Kip Thorne and Anna Zytkow first put pencil to paper. So it may be that the tool which finally confirms or dismisses these creatures has not yet been built, and that the answer waits, patient, for an instrument still to come. And I find that a strangely comforting thought to rest on, that the question is still open, that there is a real creature, or the real possibility of one, hanging out there in the dark, neither confirmed nor ruled out, waiting for us to grow just a little more able to see. So much of what we know about the sky is settled, closed, filed away. But here is a genuine mystery still in play, a star with a dead heart, allowed by the laws of nature, glimpsed perhaps in one distant giant, and not yet pinned down. Somewhere, tonight, while you lie here drifting toward sleep, there may truly be a giant glowing with a corpse at its center, keeping it secret, waiting to be found. And the people who might find it are out there too, on their mountaintops, reading their faint spectra, turning the same question over that we are turning over now, only with instruments instead of imagination. We are all, in our different ways, leaning toward the same distant light. That is the state of the science, as honestly as I can give it to you. Strong theory. Tantalizing candidates. No confirmed example. A creature the laws allow, but the sky has not yet clearly shown. And a detective's task so fine, so hedged about with decoys and difficult atmospheres and questions of distance, that the not knowing is no failure at all, but simply the true and honest edge of what we can yet reach. Now, having walked all the way around this strange house at dusk, having looked in every window we can look in, let us step back from the science itself and ask the softer question, the one that has been waiting quietly underneath all the numbers. What does such a creature mean? Not what is it, and not how would we find it, but what does it do to us to know that the universe can hold such a thing? Let us drift now toward meaning. Think for a moment about what the word star has always meant to us. For as long as there have been people, a star has meant a point of steady light in the night, a small fixed fire, a thing that shines. And when we learned, over the last century or so, what stars truly are, the meaning deepened but did not break. A star, we learned, is a great ball of gas, held up against its own weight by the fire burning at its centre, turning light elements into heavier ones and pouring out energy as it does. That is a star. A furnace held together by its own gravity. That definition has served us well, and it fits nearly every point of light you can see in the sky tonight. But a Thorne-Zytkow object, if it exists, does not fit that definition, and that is part of why it matters. It is a star with no ordinary fire at its centre. Where the furnace should be, there is a corpse, a dead star already burned out and collapsed. And yet it shines. It holds together, glows across the face of the night like any other giant. It shines by other means, by the slow rain of its own gas falling onto the dead heart, or by that exotic burning near the neutron star's surface. So here is a thing that is unmistakably a star by every appearance, and yet is powered by a mechanism no ordinary star uses, built around a centre that is itself the remnant of a star that has already died. It is a star built from a corpse. A star that keeps the light on using the grave at its own middle. And to hold such a thing in your mind is to feel the word star stretch quietly to make room for something it was never quite meant to hold. That stretching is one of the deepest pleasures the sky offers us. Again and again, when we look closely, the universe turns out to be stranger and more various than our tidy definitions allowed. We say a star is a furnace, and then we find a star that runs on a buried corpse. We say a thing cannot be both crushingly dense and nearly empty, and then we find an object that is both at once a mountain in a spoonful wrapped in a cloud you could see through. We reach for a category, and the universe gently overflows it. And rather than being troubled by that, I think we can be delighted by it. It means the sky is not yet finished surprising us. It means there is still room, out there in the dark, for creatures we have not fully imagined, for arrangements of matter that break our rules and force us to write kinder, wider ones. And there is a second meaning here, quieter than the first, that I want to hand to you gently. It is about how we came to know any of this at all. Consider what we have done tonight, or rather what the patient astronomers of the last 50 years have done. They have reasoned their way to a creature they have never seen. They have described the heart of a star they can never look into. They have measured the temperature of a surface 200,000 light-years away by the color of its glow, and its size by its brightness, and its distance by the rhythm of pulsing stars, and its true home by the faint drift of its position across the years. They have read the recipe of its outer gas from the missing colors in its light, and from that recipe alone, from nothing but the dark lines in a spread-out beam of ancient light, they have dared to ask whether a dead star sits buried at its core. They have reached the heart that no eye and no telescope can ever touch, using only the light that leaves the star and crosses the dark to us. That is, when you sit with it, a quietly staggering thing for a species to be able to do. We are small, soft creatures, bound to the surface of one small world, unable to travel even to the nearest star, unlikely ever to leave our own small corner of the sky. And yet, from here, from this one small world, we have learned to read the hidden hearts of stars in other galaxies. We cannot go there. We will almost certainly never go there. But we can know. We can reach out with patience and reason and careful measurement across distances that light itself takes 200,000 years to cross, and we can learn true things about what waits at the center of a star we will never visit. The reaching is done not with ships, but with thought. Not with hands, but with light, carefully caught and carefully read. And that too is what a Thorne-Zytkow object means. It means that patient, indirect, humble measurement can carry us to places no journey ever could. It means the mind can reach where the body never will. There is something in that worth holding close as you drift towards sleep. We so often feel small before the sky, and we are small, truly small, smaller than any number can gently say. The same smallness that cannot cross the void has learned to read the void, to weigh its stars and sound their hidden hearts from a distance, to reason its way to creatures it will never touch. Our reach is not in our bodies. Our reach is in our attention, in the slow, careful looking that turns a point of light into a whole known world. And that reach is real. It has carried us already to the buried heart of a giant in another galaxy and left us standing at the edge of a genuine mystery, not knowing yet what we will find, but knowing how to look. To be small and still able to look that far is not a sad thing. It is, I think, one of the finest things about being the kind of creature we are. So let that be the meaning we carry now, as the science falls away behind us and we begin the long, slow drift towards sleep. A star built from a corpse, keeping the light on, stretching the very word star to make room for itself. And a small, warm, wondering people, bound to one little world, who learned nonetheless how to reach across the dark and read the hidden heart of such a thing, patiently, humbly, with only the light to guide them. Hold those two together. The strange creature and the patient reaching. They belong to the same quiet wonder. And now, having reached as far as thought can reach tonight, let us begin gently to let it all go and to turn toward rest. Let us return for a while to the dead heart at the center, because we have spoken of it as a corpse and a stone and a mountain in a spoonful. But I have not yet let you feel just how extreme a thing a neutron star truly is, and it is worth feeling slowly before we let the night carry us off. This is the object buried at the core of our giant, and the more you understand of it, the more astonishing it becomes that anything could hold together around it at all. We said a neutron star is what remains when the core of a large star collapses in its death. But collapse is too gentle a word for what happens. The core falls inward in an instant, faster than thought, and the matter in it is crushed together with such violence that the ordinary structure of atoms simply cannot survive. In the world you know, an atom is mostly empty space, a tiny dense center with a haze of even tinier particles far out around it, so that all the solid things you have ever touched are, in truth, almost entirely emptiness held apart by tiny forces. But in the collapse that makes a neutron star, that emptiness is driven out. The particles are pressed so hard together that they merge, and the empty space within every atom is squeezed away, until what remains is matter with no gaps left in it at all, packed as tightly as matter can be packed this side of a black hole. That is why a spoonful weighs a mountain. It is matter with the emptiness taken out. It is what everything you know would become if you could wring all the space out of it. And the gravity at the surface of such a thing is beyond anything in ordinary experience. On the surface of the earth, gravity holds you gently to the ground, and you can leap against it and lift your arm against it and hardly think of it at all. On the surface of a neutron star, gravity is so strong that it is difficult even to speak of it in familiar terms. If you could somehow stand there, which you never could, you would be flattened beyond recognition in less time than it takes to finish this breath, pressed into the surface by a weight so immense that the whole idea of standing loses its meaning. Pebble dropped from just above the surface would strike it moving at a fantastic speed, carrying the energy of a great explosion, all gathered in the fall. The gravity is so deep that it does something you might think only a black hole could do. Bends the very path of light. Light passing near the surface of a neutron star is curved by the pull, so that if you could hover above one and look down, you would see, impossibly, a little way around its far side, the light from beyond the horizon bent up and over toward your eyes. Even light, the fastest and lightest thing there is, cannot travel in a straight line so near such a mass. That is the object at the center of our giant. A thing so heavy it bends light around itself, buried in a cloud of gas so thin it is nearly a vacuum. And it is this bottomless well of gravity that powers the lighter of our strange stars, the accretion we spoke of earlier. When gas from the great envelope drifts inward and falls toward this dead heart, it does not fall a little way. It falls down the deepest well in the star, gaining more and more energy the closer it comes, until, arriving near that crushing surface, it releases that energy in a flood of heat and light. The deeper the well, the more energy a falling thing can give up, and there is no well deeper than the surface of a neutron star, save the edge of a black hole itself. So the rain of gas onto the dead heart is not a gentle drizzle. It is one of the most powerful ways the universe has of turning falling into fire. The giant glows, in part, because its own gas is forever falling down the deepest well at its center and giving up the energy of that fall as light. There is a strange and quiet poetry in it. The star shines by feeding itself, drop by drop, into the grave at its own core, and the grave, being so deep, pays back the offering in light. And the exotic burning in the heavier stars, the rapid capture of protons near that searing surface, depends on the same extremity. It is only because the region just above the neutron star is so ferociously hot, driven up by all that crushing density and all that infalling energy, that such a rare kind of nuclear building can run there at all. In the calm core of an ordinary star, the temperature is high, but not high enough for this. Only in the fierce heat just above a buried corpse does the rapid proton process find the conditions it needs to build up rubidium and strontium and molybdenum and the rest of that strange recipe. So both engines of these creatures, the falling and the burning, trace back to the same source. The impossible extremity of the dead heart, its crushing gravity, its bottomless well, its searing skin. Take away the neutron star, and neither engine can run, and the strange elements are never made, and the fingerprint never appears, and there is no mystery to hunt at all. Everything about a Thorne-Zytkow object, all its strangeness and all its light and all its faint signature, flows from that one small, heavy, impossible thing hidden at its center. The whole creature is, in a sense, a giant wrapped around the extremity of a single dead star, glowing with the consequences of that extremity. I want you to hold, one more time, the sheer improbability of the arrangement. A neutron star is one of the most extreme objects the universe can build without tipping over into a black hole. It is dense past all sense, its gravity fierce enough to bend light, its surface a place where the ordinary rules of matter break down. And the theory says that such an object could sit quietly at the very center of a great red giant, cradled in gas so thin it is nearly nothing, and that the two of them together could go on shining, calmly for a while, as a single star. The most violent object married to the gentlest haze. Corpse of one sun keeping another sun alight from the inside. It should not be a restful image, and yet somehow, told slowly enough, it is. There is a stillness at the heart of it, a great slow calm, wrapped around a small fierce center, and I find that if I hold it gently, it steadies me rather than the opposite. The universe can build the most extreme thing imaginable, and set it, quietly, in the middle of something vast and slow and red, and let it glow there, patient, for an age. If the universe can hold that much extremity so calmly, perhaps we can let our own smaller troubles rest a while too and grow calm and drift. I would like to walk once more, slowly, through the making of this creature, because a story worth telling is worth telling twice, in a softer voice the second time, and because the slow fall at the heart of it is exactly the kind of thing a tired mind can rest against. So let us imagine it again, not as a diagram, but as a long, quiet unfolding in time. Begin with two stars, born together from the same great cloud, so long ago that the number of years is not worth speaking aloud. They come into being side by side, close enough to fall into each other's pull, and they begin the slow dance of a binary, two suns turning around a shared center, bound together for as long as they both shall shine. Picture them there, in the young dark, 2 points of fierce light wheeling patiently around one another, neither one aware, if awareness even means anything for a star, of the strange fate that waits for them. They simply turn and burn and turn. One of them is heavier, and so one of them burns faster, and so one of them dies first. Its core runs out of fuel and collapses, and the star tears itself apart in a supernova, a flash so bright that for a little while it can outshine a whole galaxy of ordinary stars. And when that flash fades, and the blown-away gas drifts off into the dark, what is left behind is the neutron star, the crushed and tiny corpse, still bound by gravity to its living partner, still turning in the old dance. The pair is changed now. One living star, one dead one, wheeling on together as if nothing has happened. And for a long, long age, that is how it stays. The survivor burns steadily. Corpse circles it, patient, dark, waiting, though a dead star cannot really wait, and I only say it that way because it is easier to feel. Then, in its own slow turn, the survivor grows old. Its own core begins to fail, and its outer layers respond by swelling, puffing outward, cooling as they spread, until the once ordinary star has ballooned into a great red giant, reaching outward across millions and then hundreds of millions of miles. And the little dead star, still circling, finds that the space it moves through is no longer empty. The swelling giant has reached out and touched it. It is inside the outer gas now. The two of them, once separate, now share a single body, a common envelope, one skin around two hearts. And here begins the long fall, and here is where I want you to slow your breathing and let the pace of it match the pace of your sinking towards sleep. Because the fall is not sudden. The neutron star, drifting now through the thin outer gas of the giant, feels only the faintest drag, the gentlest friction, almost nothing at any single moment. That faint drag never stops. Turn after turn, the neutron star gives up a little of its motion to the gas, and settles a little deeper, and turns again, and settles a little deeper still. Round and round it goes, tracing a great slow spiral inward through the body of the giant, sinking through layer after layer, each one a little denser and a little warmer than the last. It is the slowest of falls, a settling rather than a plunge, a patient easing down through the great red body of the star toward the core that waits at its center. And all the while the giant goes on glowing above, unbothered, calm, giving no outward sign of the small dark thing spiraling down through its depths. And at the very end of that long spiral, the neutron star reaches the center and merges with the giant's own core, or takes its place and settles there, and the making is done. A Thorne-Zytkow object now, a giant with a dead heart, formed not in a moment of violence, but through an age of slow sinking, a corpse drawn gently home to the centre of a living star. I find that a strangely peaceful thing to picture when I let the time scale be as slow as it truly is. Not a crash, not a catastrophe, a settling, a slow homecoming through the dark over an age longer than any story we could tell. And there was the other road too, the road of the crowd, and I want to give it its second telling as well, softly. In the crowded heart of a great cluster of stars, where hundreds of thousands of suns are gathered close and wheeling slowly around a shared centre, a lone neutron star drifts among the throng, one small dark corpse in a great slow crowd of light. And in that crowd, unlike in the lonely emptiness where we live, it can happen that the corpse passes near a great red giant, and instead of sailing past into the dark, it is caught, nudged by the gravity of the many stars around it, drawn into the giant's outer gas. And then the same long fall begins, the same faint drag, the same patient spiral inward, the same slow homecoming to the centre. Two roads then. One of partnership, two stars born together and grown old together until one is swallowed. One of chance, a lone corpse caught in a crowd and drawn down. And at the end of either road, the same quiet creature. A giant with a dead heart, glowing in the dark. And what becomes of it in the end? Because nothing in the sky lasts forever, and a Thorne-Zytkow object least of all. This is not a stable arrangement that can shine for billions of years the way a calm yellow star can. It is precarious, temporary, a phase rather than a resting place. The models suggest it would endure only for a relatively brief window of cosmic time and then change again. Perhaps the neutron star at its centre slowly grows, feeding on the gas that falls onto it, until at last it grows too heavy to hold itself up and collapses further into a black hole, and the giant is undone from within. Perhaps the great envelope is gradually lost to space, stripped away over time, until the dead heart is laid bare once more, a lone neutron star again, its brief marriage over. We do not know for certain which fate waits because we have never watched one of these creatures live out its life, and everything we say about its ending is, once again, a model and not an eyewitness account. But whatever the ending, it is brief. Creature forms slowly over a long age of falling, and then shines only for a little while, and then passes on into whatever it becomes next. Rare to make, quick to change, here and then gone in the slow reckoning of the sky. There is a gentleness in that too, if you let there be. Everything in the universe is passing, even the strangest and most extreme of things. Even a star built from a corpse shines only for a while, and then lets go and becomes something else. Nothing holds its shape forever, not the giants, not the dead hearts buried in them, not the great slow spirals that made them. All of it is moving, changing, coming together and coming apart, over ages so long they make our whole history a single breath. And that is not a sad thing to fall asleep on. It is, I think, a kind of company. We are not the only passing things. We are in the good company of stars, all of us here for a while and then gone, all of us shining in our own small way for as long as we are given and then letting go and becoming something else. To rest tonight is only to do, softly and for a few hours, what the whole universe is always doing. Letting go. Changing. Passing gently on. I want to follow a single beam of light now, all the way from the strange star to your eyes, because when you understand the journey that light makes, the whole business of measuring a distant star becomes something you can feel in the body rather than only think in the head. And it is a good, slow thing to follow as the night deepens. The light begins deep inside the giant, born in the churning gas, carrying with it the marks of the elements it has passed through, those faint gaps in its colors where the strange atoms have drunk their fill. It works its way up through the last of the envelope and leaves the surface of the star, setting out into the dark. And now it simply travels. There is nothing to slow it and nothing to stop it, only the vast emptiness between the galaxies, and the light crosses that emptiness at the greatest speed the universe allows, the speed beyond which nothing can go. And still, at that unthinkable speed, the journey takes about 200,000 years. Let me try to make that span of years something you can hold. When this light left the star, there were no cities anywhere on Earth, and no farms, and no writing, and no history of the kind we keep. People who lived then left us no words, only bones and stone tools, and the faint traces of old fires. The great cave paintings had not yet been made. Oldest story anyone has ever told had not yet been told. And in that ancient world, on a night much like this one, the light you might gather tonight was already halfway across nothing, already old, already travelling. It has been falling toward us through the entire length of everything our kind has ever done. Every empire that ever rose and fell, every song ever sung, every person who ever lived and loved and was forgotten, all of it happened while this one beam of light was crossing the dark toward us. And only now, tonight, does it arrive. That is what it means to look at a star 200,000 light years away. You are not seeing the present. You are seeing a message sent before your people had a single word, arriving at last, tonight, at your window. And when it arrives, it is very faint, because light spreads and thins as it travels, growing dimmer with distance, until the glow of a whole giant star, blinding at its source, is reduced to the faintest whisper by the time it reaches us. This is why we need great telescopes with mirrors wider than a room, high on dry mountain tops above most of the blurring air. Telescope is, in the end, a bucket for light. The bigger the mirror, the more of that faint ancient light it can gather, drop by drop, and pour into the instruments that spread it into its colours. The great telescope in the mountains of Chile that read the light of our candidate has a mirror more than 20 feet across, a single curved surface of glass, gathering the 200,000-year-old whisper of a star and concentrating it enough to be read. And even then, It takes patience. The light is so faint that the telescope must hold steady on the star for a long while, gathering, letting the faint beam build up until at last there is enough of it to spread into a spectrum and study. So the reading of a single distant star is not a glance. It is a long, still watching on a cold mountain under the darkest skies on earth, catching the last of a light that set out before history began. I find something almost unbearably tender in that, and I mean tender in the way that makes you calm rather than sad. Think of it. A star, unimaginably far, glowing with a secret at its heart. A light leaving that star before your ancestors had a word for star. That light crossing the whole dark gulf between two galaxies for 200,000 years, thinning as it goes. And at the very end of that long, long journey, a small warm creature on a small warm world, having built for itself a great glass eye and carried it to a mountain top, catches the last faint trace of that light, and reads in it the story of a dead heart buried in a living giant. The whole reach of it, from that star to your understanding, is one unbroken thread of light. Nothing carried the message but the light itself, and we learned somehow to read it. Let me re-anchor the great size of the thing one more time in a new image, because these numbers reward being turned over slowly, and there is comfort in restating a wonder until it softens into something you can rest against. We said the neutron star is only about 12 to 15 miles across, and that the giant around it could be hundreds of times wider than the sun. Try it this way. If you shrank the giant down until it was as wide as a great city, wide enough that crossing it would take you a long day's travel, then on that same scale, the neutron star at its center, the dead heart, would be far smaller than a single grain of sand, dropped somewhere in the middle of the city and lost at once from sight. And yet that invisible grain of sand would weigh more than the entire city around it, more than every building and every street and every hill of that whole shrunken star. Or try it another way. Line up our suns, one after another, to reach across the giant. Take hundreds of them, laid side by side, to span from one edge of that great red star to the other. Hundreds of suns in a row to cross a single star. And at the center of all that, a corpse the size of a town. However you turn it, the same wonder falls out. The vast wrapped around the tiny, the living wrapped around the dead, the gentle wrapped around the extreme. And however far it is, however faint its light, we have found a way to reach it. Not with ships, which could never make the journey, not in 100,000 lifetimes, but with light and patience, and the slow, careful reasoning that turns a faint whisper of colour into the knowledge of a hidden heart. We are very small, and the star is very far, and the light is very faint, and yet the thread between us holds. That is the quiet triumph underneath all the numbers. Across 200,000 years of dark, the thread of light holds, and we have learned to read it. Now let us set the reading aside, and the reaching, and the numbers, and let the night take us the rest of the way. Let us drift now toward the softer country at the end of the journey, where the science falls away and only the wonder remains. So here we are, at the far end of the science, where the numbers grow quiet and only the feeling of them remains. We have walked all the way around this strange creature, the giant with the dead heart, and we have looked in every window we know how to look in, and now, as the night settles fully over us, let us simply rest in what it all means, without needing to measure anything more. There is a particular kind of smallness that comes over you when you sit for a long while with the true size of things, and I do not think it is a sad smallness, though it can feel that way at first. Consider where you are. You are lying somewhere on the surface of one small world, a world of stone and water and air turning slowly in the dark. That world circles one ordinary star, our sun, which is itself only one among hundreds of billions of stars in our galaxy, all of them wheeling slowly around a shared center over spans of time too long to feel. And our galaxy is only one among many billions of galaxies scattered through a universe so wide that light itself, for all its speed, cannot cross even the part we can see in anything less than an unimaginable stretch of ages. Somewhere in all of that, perhaps in our own galaxy, perhaps in that small companion galaxy 200,000 light-years away, there are these rare and hidden creatures, giants with dead hearts, glowing quietly, keeping their secret. And you, lying here, are smaller than any of it, smaller than a grain of sand on the shore of an ocean that has no far side. And yet here is the thing I want you to feel softly as you begin to let go. That same smallness is not separate from the vastness. It is part of it. You are not a stranger looking in at the universe from outside. You are made of it. The atoms in your body, the iron in your blood, the calcium in your bones, the very calcium we listened for in the light of that distant giant, all of it was made inside stars, forged in their hot hearts or in their violent deaths, and scattered out into space and gathered up again over ages into the world that became your world and into the body that became your body. You are not looking at the stars from the outside. You are the stars, grown quiet and warm and awake, lying here in the dark, wondering about yourself. The same universe that builds a giant around a dead heart built the mind that can wonder what such a thing might be. You are one of the ways the universe has found to look at itself and to ask what it is. I think that is worth resting on when the smallness threatens to feel lonely. You belong here. You are not an accident perched on the edge of an indifferent vastness. You are woven right into it, made of the same stuff as the stars you are wondering about, kin to the giant and even, in a strange and distant way, to the dead heart buried inside it. Corpse at the center of that far-off star, and the warm living heart beating in your own chest are made of the same kinds of matter, obeying the same laws, part of the same one great unfolding. Across all that distance, across 200,000 years of dark, you and the strange star are relatives. You are both the universe, taking different shapes for a while. And there is a peace to be found in being small once you stop fighting it So much of the weight we carry through our days comes from feeling that everything rests on us, that our worries are enormous, that our troubles fill the whole sky. Lie here for a moment under the true sky, the real one, the one with the hundreds of billions of stars and the billions of galaxies and the rare hidden giants with their dead hearts, and feel how gently your troubles shrink. Not because they do not matter. They matter in their place to you, and that is right. But against the true scale of things, they soften. They find their proportion. The universe has been unfolding for an unthinkable span of ages, building and unmaking stars, spiraling corpses slowly into the hearts of giants, and it will go on unfolding for ages longer still, long after this night and all our nights are over. And you are allowed tonight to set your small weight down for a few hours and to let the great slow turning of everything carry you the way it carries the stars, without your having to hold any of it up. To rest beneath the infinite is to feel carried by it, rather than crushed by it. That is the turn I want you to make now, gently, as sleep begins to come. To feel small and alone beneath a cold and enormous sky, but to feel small and held, a warm and living part of something vast and patient and old. The same gravity that pulls the gas down onto the dead heart and lights the giant from within is the gravity that holds you to your bed tonight, that keeps your world beneath your feet, binds the whole great turning together. You are not outside it. You are held inside it, one small warm part of a universe that knows how to make dead hearts glow, and knows too how to make a creature like you who can lie in the dark and wonder about and be at peace. So let the wondering slow now. Let the questions, which have carried us so far tonight, grow soft and unhurried, the way questions do at the very edge of sleep, when you no longer need the answers, only the gentle turning of the thoughts. Is there truly a giant out there with a corpse for a heart? Perhaps. Perhaps not. No longer needs to be decided tonight. It is enough that the universe could hold such a thing. It is enough that we have reached toward it and stood at the edge of finding it and come away with wonder if not certainty. The not knowing is a soft place, and you are allowed to rest in it. You do not have to solve the sky tonight. You only have to lie beneath it and breathe and let it carry you. Let your breathing slow now, if it has not already, and notice how quiet the room has become around you. Notice the weight of your body against whatever holds it, the bed or the chair or the pillow, and how the ground beneath all of that holds it in turn, and how the world holds the ground, turning slowly in the dark. You are held by layer upon layer of gentle things tonight, all the way down and all the way out to the great slow turning of the galaxy itself. I want to give you, as the night deepens, a few soft images to rest against, images pulled from the long journey we have taken, so that if your mind wanders as you drift, it has calm places to wander to. Picture the giant, first the great red star, glowing softly in the dark, cool at its enormous surface, so vast that whole worlds could be lost inside it. Do not think now of the numbers or the measuring, or the arguments. Just see the red glow of it, steady and slow and ancient, hanging in the black, patient as a banked fire in the last hour of the night. Let it glow there in your mind, warm and dim and calm. And then, if you like, sink slowly toward its center, the way the dead heart once sank, in that long, slow spiral we followed. Down through the thin outer haze, gentle as mist. Down through the deeper layers, warmer and slower. Down toward the quiet center where the corpse rests, held in the middle of all that glowing gas, small and heavy and still. There is no violence in the picture now, only stillness, only a small dark heart at the center of a great soft light, resting as you are resting. The most extreme thing in the universe, wrapped in the gentlest, holding perfectly still at the center of a slow red glow. Let yourself be that still. Let yourself grow heavy and quiet at your own center, held by all the soft layers around you. Or picture the light, if you would rather, the long thread of light we followed across 200,000 years of dark. See it leaving the star, faint and old, and crossing the great emptiness, patient, unhurried, in no rush at all, taking as long as it takes, ages upon ages, drifting steadily toward a small warm world it does not know is waiting. There is no anxiety in that light. It simply travels at its own steady pace for as long as the journey takes, and arrives when it arrives. You might let your own thoughts travel like that now, unhurried, in no rush, drifting steadily towards sleep, taking as long as they take, arriving when they arrive. There is nowhere you need to be tonight. There is nothing you need to reach. Like the light, you may simply drift at your own quiet pace through the dark toward rest. Everything out there is moving so slowly on such patient timescales that our whole frantic hurry begins to look very small beside it. A neutron star spirals into the heart of a giant over an age longer than all of human history. A beam of light crosses between two galaxies over 200,000 years. The galaxies themselves turn once in spans of time so long that our sun has made only a couple of dozen such turns in its entire life. Nothing out there is in a hurry. The universe is the least hurried thing there is. It has all the time there could ever be, and it spends it slowly, building and unmaking its stars over ages, in no rush at all. And you are part of that unhurried thing. You are allowed, tonight, to move at its pace, to let go of the hurry, to let the slowness of the stars become, for a few hours, the slowness of your own breath, your own heartbeat, your own drifting mind. Feel your body grow heavier now, limb by limb, the way gas settles slowly toward the center of a star. Let your shoulders soften and sink. Let your hands lie still and open. Let the small tightness go from your jaw, from around your eyes, from the space between your brows where the day's worries gather. Let all of it grow heavy and warm and still, sinking gently, like the slow settling of matter toward the quiet center of things. There is nothing to hold up now. There is nothing to reach for. The great slow turning of everything is holding you as it holds the stars, and you may let go and be held. And if a thought comes, some worry from the day, some small unfinished thing, let it be like the faint drag on the neutron star, gentle, passing, nothing you need to fight. Let it drift through, and let it settle, and let it sink away into the quiet, the way everything sinks away into the quiet in the end. You do not have to chase it or solve it or hold it. You may simply let it pass and return to the soft red glow, or the slow thread of light, or the warm weight of your own resting body held in the dark, carried by the patient turning of it all. The giant glows on, out there in the dark, keeping its secret, in no hurry to be understood. The light crosses the emptiness, patient, taking all the time there is. The galaxies turn, slow and vast and calm. And you lie here, small and warm and held, one living heart among the countless things the universe has made, allowed at last to rest. You have wondered enough for one night. You have reached far enough. Now you may simply be here, breathing, heavy, quiet, carried, while the great slow universe goes on turning gently all around you and asks nothing of you at all but that you rest. There is one image from tonight that I keep returning to, and I think it may be the one to carry down into sleep with you, because it holds so much in so small a space. It is the image of a star built from a corpse. A ghost keeping a giant alive from the inside. Let us sit with it a little longer, softly, and see what it has to give. By every ordinary rule, a dead star should be the end of something. A neutron star is a remnant, a leftover, what is finished when a great star has spent its life. It is a grave marker. And yet, in a Thorne-Zytkow object, that grave marker becomes the very thing that keeps a new light burning. Corpse at the center is not merely buried and forgotten. It is the engine. Its crushing gravity draws the giant's gas down and turns the falling into fire. Its searing surface makes the strange new elements that no ordinary star can make. Without the dead heart, there would be no light, no strange recipe, no creature at all. The end of one star becomes the source of another star's glow. The grave keeps the light on. I do not want to make too neat a lesson of it, because the universe is not a fable and does not owe us tidy meanings. But I will let the image do its quiet work, and you may take from it whatever your drifting mind wishes to take. There is something in it about how endings are not always only endings. About how the things we think are finished can become, in ways we do not expect, the foundation of something still glowing. About how even a corpse, in the strange economy of the stars, can keep a great warm light burning long after its own life is over. It is not a promise. It is only an image offered gently for you to rest against. The dead heart glowing at the center of the living giant. The end that keeps the light on. And there is a companion image, just as gentle, and it is about the giant, not the heart. Because, from the outside, remember, the giant looks entirely ordinary. It looks like just another red supergiant, one more warm red lantern among the many. You would never guess, looking at it, what strange and extreme thing it carries hidden at its centre. It simply glows, calm and vast and red, keeping its secret without any show at all. And I find that a tender thing to think about, drifting here in the dark. How many of the quiet, ordinary-seeming things around us carry, hidden at their centres, something extraordinary that never shows on the surface? How much is held quietly, without display, behind the plainest faces and the plainest lights? The giant does not announce its dead heart. It just goes on glowing. And perhaps there is a gentleness in that too, a permission to let your own hidden weights be carried quietly, without needing to be shown, while you simply go on glowing warm and ordinary and calm in the dark. Two of the patience that this whole story asks for and rewards. Kip Thorne and Anna Zytkow imagined this creature nearly 50 years ago, from the laws of physics alone, with no example anywhere in the sky. And they did not get to see it confirmed. Anna Zytkow lived to help point at the best candidate ever found, decades after the first imagining, and even that candidate remains disputed to this day, neither confirmed nor ruled out. Half a century of careful thought, and the answer is still open. And yet the work was not wasted, not for a moment. Every year of it added something, sharpened something, taught us how to look a little better. The theory grew richer. Tools grew finer. Candidate was found and questioned and studied again, and the questioning itself taught us more than a quick, easy answer ever could have. This is what patience looks like in the search to understand the sky. Not a single triumphant discovery, but a long, slow accumulation, carried faithfully across careers and generations, each person handing the question on to the next, a little clearer than they found it. There is comfort in that for anyone who has ever felt that their own patient work might come to nothing. The astronomers who have spent their lives on this question do not know, even now, whether these creatures truly exist. And still they look, and still the looking is worthy, and still each careful measurement is a real gift laid down for whoever comes next. The value was never only in the finding. It was in the looking, in the caring enough to look well, in the passing on of the question a little clearer to the next patient mind. And someday, perhaps long after all of us are gone, someone with an instrument we have not yet dreamed of will point it at a distant red giant and settle the matter at last. And they will do it standing on 50 years, 100 years of patient work by people who never got to know the answer. That is how the sky is truly won. Lowly, patiently, together, across more time than any one life holds. So if you have ever wondered whether the slow, patient things you do, the careful, small work no one applauds, matters in the end, the astronomers and their dead-hearted stars be your quiet answer tonight. It matters. The looking matters, even when the finding never comes in your own time. Care matters. The passing on of it a little clearer to whoever comes next matters most of all. You are part of a long, slow, patient reaching, all of you, all of us, and the reaching is worthy whether or not you live to see it arrive. Let that be a soft thing to rest on. Your patience is not wasted. Nothing careful and kind is ever wasted. It is all handed on a little clearer into the great slow turning toward an arrival you may never see, but that your care helps to make possible. And that is enough. That is more than enough. You may rest now, knowing it is enough. Let me bring the story home now, out of the far distance and back to the sky. You could actually step outside and see tonight, 'cause there is a gentle comfort in knowing that the wonder we have been chasing is not entirely out of reach of your own eyes. It lives, in a way, right there above your roof. If you have ever looked up at the winter sky and found the great figure of the hunter, with his 3 bright stars in a row for a belt, then you have already seen, with your own eyes, a red supergiant. For at one shoulder of that hunter burns a star called Betelgeuse, and it glows a deep and unmistakable orange red, easy to pick out once you know to look for it. Betelgeuse is one of these great red giants, cool at its enormous surface, so vast that if it were set down where our sun sits, it would swallow the inner worlds much as we have described all night. It is not a Thorne-Zytkow object, as far as anyone knows. It is, by all appearances, an ordinary red supergiant with an ordinary burning core, living out the late chapters of its life. But it gives you a real and visible picture of the kind of star we have been speaking of. The next clear night, you can go out and find that red shoulder in the sky and know that you are looking at a true giant, the same kind of great red lantern that, somewhere else, might hide a dead heart at its center. The wonder is not only in the textbooks. It is hanging there over your own head, waiting. And if you live far enough south, and far enough from the glow of any city, you might even find, low in the sky, that soft dim smudge of light we spoke of, the Small Magellanic Cloud, the little companion galaxy where our best candidate was found. To the eye, it is only a faint patch, easy to miss, easy to mistake for a stray cloud. But it is a whole galaxy, hundreds of millions of stars, 200,000 light-years away, and within it, perhaps, glowing too faintly for your eye to single out, is the very star we have followed all night, HV 2112, keeping its disputed secret. You could stand in a dark field, on the right night, in the right part of the world, and look with your own unaided eyes at the faint glow of the galaxy that holds the best candidate anyone has ever found for a star with a corpse at its heart. You would not see the star itself. It is far too faint for that. But you would see its home, the soft, dim cloud that holds it, and you would know that somewhere in that faint patch of light the mystery we have wondered about all night is quietly waiting to be solved. I love that the wonder reaches all the way down to what your own eyes can hold. So much of astronomy is done with great machines on cold mountain tops, gathering light too faint for any person to see. And that work is precious, and it is how we learn the deep things. But it is good to remember that the sky is not only in the machines. It is right there every clear night for anyone who steps outside and looks up. The red shoulder of the hunter, the faint smudge of a companion galaxy, the great pale band of our own Milky Way spilling across the dark on the clearest nights, the combined light of countless stars too far and too faint to see one by one, blurred together into a soft river of light. All of it is there, for free, for anyone, waiting to be looked at with a little wonder. And knowing what we now know, even a glance at the night sky becomes richer. That red star is a giant. That faint smudge is a galaxy. Pale River is 100 billion suns. The sky has always been this astonishing. We are only now, slowly, learning to see it. So the next time you cannot sleep, or the next time the night is clear and you have a moment to step outside, you might go and find these things. The red giant on the hunter's shoulder. Faint companion galaxy low in the south, if your sky allows it. The great pale band of the Milky Way. And you might remember, standing there in the dark, that hidden among all that light, rare and quiet and hard to find, there may be giants with dead hearts, glowing calmly, keeping their secret, waiting patiently for us to grow able enough to find them. You will not see them, but you will know they might be there. And that knowing, that quiet company of wonder, is itself a kind of gift, one you can carry with you into any night, and rest against whenever the dark feels empty. The dark is not empty. It is full of strange and patient marvels, more than we have found, more than we have imagined, waiting in the light that falls on you every clear night of your life. For now, though, you do not need to go outside. You only need to lie here and let the sky be where it is, over the roof, over the clouds, turning slowly through the dark as it always does, whether you watch it or not. It does not need your watching. It will keep its giants and its galaxies and its dead hearts safe through the night, and they will still be there in the morning and every night after. You may rest and let the sky keep itself. It has been doing so for longer than there have been eyes to watch it, and it will go on, patient and vast and full of quiet marvels, while you sleep. There is a thought I have been saving for the quietest part of the night, and I think this is the moment for it, when your mind is soft and your body is heavy and you are more than half the way towards sleep. It is this. The universe is under no obligation to be understandable. And yet, again and again, it turns out that we can understand it, if we are patient enough and careful enough and humble enough about what we do not yet know. Think of how strange it is that any of this works at all. Creature is imagined from equations, decades before anyone looks for it. The laws of physics, written down by human hands, predict that a certain arrangement of matter should be possible, should glow in a certain way, should carry a certain recipe of elements. And then, when we go out into the sky and look, we find that the laws were right, or nearly right, that the universe really does seem to build such things, that the light of a distant star really does carry, faintly, the very fingerprint the equations foretold. There was no reason it had to be this way. The universe did not have to be the kind of place whose deep workings a small warm creature on a small warm world could ever hope to grasp. And yet it is. The dark lines in the light really do tell us what a star is made of. Colour really does tell us its heat. Pulsing of distant stars really does tell us how far away whole galaxies lie. The universe speaks quietly in a language we have slowly learned to read, and it keeps its promises, and it rewards our patience with understanding. That is a gift so large we mostly forget to notice it. And yet, for all we understand, the universe keeps a great deal hidden, and the Thorne-Zytkow object is a fine example of the balance. We can predict it. We can describe its structure, its two births, its strange engines, its faint fingerprint. We can point to a candidate and study it for years. And still, after all of that, we do not know for certain whether even one of them exists. The universe gives us enough to reason with and enough to reach toward, and then it keeps the final answer just past our fingertips, waiting. There is a perfect gentleness in that arrangement, if you think about it kindly. We are given enough to wonder well, but not so much that the wondering ever ends. The mystery is never quite used up. There is always a little more, just past the edge of what we can see, to keep us reaching, and reaching keeps us awake and alive to the world in a way that easy answers never could. So do not be troubled, as you drift, that we could not settle the question tonight. Be glad of it. A universe with no mysteries left would be a smaller, colder place than the one we actually live in. Open question. The giant that might or might not have a dead heart. The candidate still argued over. The creature still unconfirmed after 50 years of looking. All of it is a sign of a universe still generous with wonder, still holding things back to be discovered, still worth waking up to and worth wondering about. You live in a universe that is not finished revealing itself. That is a lucky thing. That is a warm thing to fall asleep inside of. And let me restate the great scale of it all one last time, softly, the way you might smooth a blanket one last time before you settle. Because the scale is where all the wonder began, and it is a good place to let it end. A dead star, only about 12 miles across, a spoonful of it heavy as a mountain, buried at the center of a giant so vast it could swallow the inner world's whole. Giant glowing softly in a galaxy 200,000 light-years away, its light setting out before your people had a single word, arriving only tonight. A faint recipe of strange elements, rubidium and molybdenum and lithium, written into that light, the only sign that leaks out from the hidden heart. And a small worn creature on a small warm world, lying in the dark, able somehow to read that sign, to weigh that giant, to sound that dead heart across all that distance with nothing but patience and light. Hold all of it together once more, gently, and then let it go. The vast and the tiny, the dead and the living, the far and the near, the known and the still hidden, all of it, one great quiet wonder, and you, a small warm part of it, allowed at last to rest. You do not have to carry any of it now. You have looked far enough tonight. You have wondered enough. The giant will glow on without your watching. The light will arrive whether or not you are awake to read it. The question will wait, patient, for the morning, and for all the mornings after, and for the patient minds still to come. There is nothing left for you to do tonight but breathe and grow heavy and let the great slow turning carry you down into sleep. Wherever you are listening from tonight, I would like you to know that you are not alone in this quiet. Somewhere, in a bright city where the stars stay hidden behind the glow of the streetlights, someone else is lying awake, wondering, listening to the same slow voice, drifting toward the same rest. And somewhere else, in a quiet stretch of countryside where the Milky Way spills overhead like a river of light, someone else is lying beneath the true dark, watching the very sky we have been speaking of, and letting it carry them down toward sleep. Near and far in the city and in the country, in the light and in the dark, there are people all over this small, warm world, settling into the night at this very moment, each of them small, each of them wondering, each of them held by the same great turning. And you are one of them. Whatever kind of night is outside your window, you are part of that quiet company tonight. I find that a gentle thing to rest on at the very end. That the wondering we have done tonight is not a lonely thing, but a shared one. All over the world, in every age, people have looked up at the same stars and felt the same smallness and the same awe. The particular knowledge is new, the dead hearts and the distant candidates and the spacecraft that map the drift of stars, but the wonder is very old. It is the oldest thing we do, older than any city or any language, this looking up into the dark and feeling both tiny and somehow held. You are doing tonight what your most distant ancestors did on nights just like this one, 200,000 years ago, when the light we now gather was only setting out. You are looking up and wondering and letting the vastness carry you. It is one of the truest things a person can do. And it links you across all that time to everyone who has ever done it, and to everyone who ever will. So let me say thank you quietly for spending this long night wandering with me, all the way out to a giant with a dead heart in a galaxy 200,000 light-years away, and all the way back again to your own dark room, your own warm bed, your own slow breath. It has been a good long journey, and you have come to the end of it, and now there is nothing left but rest. If this quiet hour has been a comfort to you, I would be grateful if you tapped like or subscribed, so that others who need a calm voice in the dark can find their way here too, and join the quiet company on some sleepless night of their own. But that is for the morning, or for whenever you wake. For now, there is only rest. The questions grow quiet now. Let the numbers fade. The giant and its dead heart drift off into the soft distance where all the night's thoughts go. You do not need them any more tonight. You have held them and turned them over and let them fill you with a little wonder, and now you may set them gently down, the way you set down anything heavy at the end of a long day, and let your hands lie open and empty and still. There is nothing left to carry. There is nothing left to solve. There is only the dark and your slow breath and the great patient turning of everything holding you softly while you sleep. And so the journey that began beneath the stars circles back to where it started. Remember how we began, a long while ago now, with a clear, cool night and the stars coming out one by one, and somewhere out there a star that was not quite a star, an old and gentle giant with something small and heavy and dead waiting at its center. We have wandered a long way since then. We have followed the corpse into the chest of the giant, down the long, slow spiral through the shared skin. We have learned how such a thing keeps its light on, feeding on the grave at its own core. We have read the faint recipe written in its light and weighed it and sounded it and stood at the very edge of finding it and come away with wonder if not certainty. And now, at the end of it all, we come back to that first clear night, and the stars still coming out one by one, and the great gentle giant still glowing softly in the dark, keeping its secret, patient as ever. Nothing about it has changed out there. The giant glows on. The dead heart rests at its center, small and heavy and still. The light crosses the long dark toward us in no hurry at all. It was there before we began to wonder tonight, and it will be there long after we have fallen asleep, and long after we have woken, and long after all our nights are over. There is a great steadiness in that, a great calm. The wonder does not depend on us. The sky keeps its marvels whether we watch or not. And so we may let go of watching now and simply rest, knowing the giant will glow on without us and be there still whenever we wish to return to it. And you might return to it on some other quiet night when sleep is slow to come. You might rest here with us again and wander out towards some other strange corner of the sky and let another long, slow story carry you down into the dark. Or you might share this quiet moment with someone you love who also lies awake sometimes and needs a calm voice and a little wonder and a way to let the day go. There is always another night, and always another marvel waiting in the dark, and always a place here for you to rest whenever you need it. But for now, there is only this night, and this rest. So let your breathing slow. Let it grow soft and even and deep, like the slow turning of a distant galaxy, in no hurry at all. Let your body grow heavy, limb by limb, sinking gently down, held by all the soft layers beneath you and around you and above you, all the way out to the patient turning of the stars. Let the last of the day's weight slip from your shoulders, from your hands, from the space between your brows. There is nothing more to hold tonight. There is nothing more to reach for. The giant glows on in the far dark. The light crosses the emptiness, patient and old. The great slow universe turns gently all around you and holds you, small and warm and safe, one living heart among all its countless marvels, and asks nothing of you now but that you rest. Sleep well. Rest easy beneath the infinite. And good night.